Good morning, Astronomy 1020. Welcome to your first homework session of the Summer 1 2021 semester. Today will be our first long day. We're going to do a homework, then we're going to do a big old 3-hour lecture, and then we're going to do a lab on the celestial spheres. I'll try to include I know, it's going to be intense, but we'll include little breaks along the way to keep you hydrated, caffeinated, and all the rest of it. Let's try to get right into homework number 1, waste as little time as possible. Calculators. I know Ryan and Ryan have one. Sage, yeah, hot pink. All right. Brandon, I don't know what's up with you in the shadows there, but I hope you have a calculator as well.
Yes, and I got mine yesterday.
Excellent. And all of you watching at home later on, you'd better have your calculators. And I can't keep an eye on you, but you better be punching too. When we do the punching, that's what this is all about. I already know how to do math. I'm not doing this for me. I'm doing it for you. So you got to punch into your calculators when I tell you. Let's make sure homework 1 is activated. I'm not 100% sure I did that. At some point, I'll activate them all. Okay, so this looks like it's enabled for you guys. Why don't you guys do me a favor and open up both of these PDFs so that you guys have the questions. Another thing that you could do is, if you want, you could also open up the PDF for today's lab. I believe we'll end up doing the first page and the second page, 3-3 and 3-4. That'll probably be all we have time for today. But at some point, you can hit print on that. I know some people's printing game takes a while. All right. So as you guys know who have taken classes with me before, I like you guys to read the questions. And let's sort of format our homeworks in the proper way. Half of doing the homework with me is actually just about learning how I want it formatted. Now, you can keep this right in your notebook because at the end of class, of course, you're just going to take a picture and you're going to submit it. But it's still a good idea to have some information at the top so that I can see your name, what class you're in, and most importantly, you want to keep track of what the homework number is, so that if later on we have any disputes about whether you turned something in or not, you'll be able to go through your notebook and find that homework. So let's put our name. Let's put Astronomy 1020. This is homework number 1. It's going to have problems from 2 different chapters in the book. Chapter 1 and chapter 2. Some of the problems we have covered. Some of them we haven't, but I've got a lot of veterans here, so I think that's going to make things a bit smoother than average. Let me take a peek again at our numbers. From chapter 1, we're doing 42 and 49. From chapter 2, we'll be doing 53, 55, and 58. All right, Ryan, since you're now a part of the gang, I'm going to have you lead us off if you don't mind. And would you be willing to read us chapter 1, number 42?
Yeah.
All right.
Scaling the local group of galaxies. Both the Milky Way galaxy and the Andromeda galaxy, M3I, have a diameter of about 100,000 light years. The distance between the 2 galaxies is about 2.5 million light years. A, using a scale on which 1 centimeter represents 100,000 light years, draw a sketch showing both galaxies and the distance between them to scale.
Ryan, let's pause there for a second.
Yep.
Okay, as veterans know, and as maybe Sage has seen before, when we're doing a tricky word problem, it's always a good idea. I like to, as a style point, I like to extract my givens. I like to get all the hard information right out on the page so I can have that at my disposal and think about it. We have the Milky Way and Andromeda, which are sister galaxies. They both have a diameter of 100,000 light years. And their distance from one another is, what was it? Was it 2.5 million light years, Ryan?
Yeah.
All right, and we'll put that right into scientific notation. You guys already know how to do that, so I'll just plop the old times 10 to the 6 on there. And in part A, we actually have to draw a sketch, a scale model in which 1 centimeter is equal to the diameter of the galaxy, 100,000 light years. You will remember from my discussions with you on Tuesday that I like to put the prime above the centimeters. What was the point of that again?
So we know which measurement is to scale and which is the one that we started with as a given.
Yeah. Or another way to say what you said, Sage, is this is real, that's reality. And the prime tells us that it's the model, right? Of course, there is a real conversion from light years into centimeters, and it ain't 1, right? 1 centimeter is not actually equal 100,000 light years. But although you wouldn't suspect that you would confuse that, as we do more and more dimensional analysis, it's possible to get, wait, which unit am I dealing with here, the model or the real ones? This is, wisdom has borne this out. Okay, I don't know if any of you actually got one of those little cheapo plastic rulers, but this would be a real good time to bust it out, because I actually want you to do the problem right and draw it to scale. Do you guys have some kind of a ruler around? How about you, Ryan? Spavid.
I need to go find one. I think I have one in a drawer somewhere. I'll be right back.
Yeah, go grab
I
a
have one
ruler.
on hand.
Awesome. Oh, you didn't get the plastic one. That's, I like the
Yeah.
clear. The clear plastic one is good because you can see what you're doing underneath it.
I just had it in the house.
Good. That's great. I think a ruler should be in every house. All the people watching at home while we're stalling here, I'm trying to think of something in your household that might have a width of 1 centimeter. If for some reason you can't find a ruler in your house, I bet you could even get one on your iPhone, a little app with a ruler. You guys will notice that 1 centimeter is approximately the width of my pinky fingernail. So if you're really hard up, Ryan, I'm going to show everyone how I want them to draw this in just a second. Let me pause the video until those guys get back. Okay, now that everyone's found a ruler, here's what I'd like you to do. We're going to need a bit of paper here. So I'm going to draw mine at a slightly different scale because I'm working on this big old board. But somewhere up in the left-hand corner of your page, let me show you how to make a galaxy. Make a diagonal line, okay? That's 1 centimeter in length. And here's a cute little trick for making a galaxy. You can put a big bulge in the center, and then you can kind of put some spiral arms on either side. So there's your galaxy. And this, of course, is 1 fake centimeter. Or 1 real centimeter that's fake. Okay. Now, here comes the fun part. We know the distance is 2.5 million light years. Our job is to figure out how many fake centimeters that line needs to be. What's the technique that we're going to use to solve that problem? Say it loud and proud, Sage.
I wasn't sure I was going to check, but I think it's dimensional analysis.
Yes, sir. Yes, it is.
Okay.
Okay, mathematician that you are, why don't you lead us off and you can take us through this by the paces. Now, you might, just from a bit of math training, kind of already know what to do, but let's do it a dimensional analysis style, okay? So tell me what to write. And yeah, follow the steps just to be on the safe side. Do you have those written down somewhere?
I was using the wrong notebook yesterday.
Oh, geez.
So the first thing we're going to do is we're going to write down the number to convert.
You're missing a part there. Oh, don't tell me you're a sloppy note taker, are you? Are you one of those?
That's what I had for number 1.
Ryan, Dick, do you have anything different?
I
Ryan?
believe so.
Other Ryan? Jesus, K. Rice, does anyone have number
Write down
1?
numbers to convert with units.
That's it. You don't just write down the number, Sage. What do you think? This is a freaking math class? You think we're lost in some abstract
I
reality?
have it
No,
written down, I swear.
we're in outer space, okay? All right, write down the number to convert with its units. That matters. All right, so what do I write down, Sage?
So that's going to be 100,000 light years.
False.
1 centimeter.
That is
Correct.
not what we are trying to convert.
Okay.
We might have gotten a little lost in the sauce with our ruler hunt. Let's take a quick peek at that problem again. It says, what's this number again? Yeah. How far from the Milky Way galaxy would the Andromeda galaxy be on this scale? So part of problem solving is trying to figure out what it is that you're actually doing or trying to convert. It is not 100,000 light years, but is instead, anyone?
2.5 times 10 to the 6.
Wow, you just love these abstract numbers, don't you, Sage? You're missing something. You're only half right. You're trying to convert 2.5 times 10 to the 6. These math guys, you gotta love them.
Light years. I said light years the first time. I swear.
I think you muted yourself. You have a hot trigger button there. You muted yourself. I didn't hear it, and I was
Talk a
listening.
lot, so I try to like cut down my noise.
No, that's okay. Bring the noise, okay? We can have a little noise here.
Okay.
2.5 million light years is how we start. What's step 2?
Let's multiply by a division bar.
That's easy. Step 3?
Put the units in first and cancel them out. So we're going to put light year on the bottom, and we're trying to convert to centimeters, but I don't think we have a rule for that.
Let's worry about that part next.
Okay.
What do we want to convert into?
Probably meters, maybe.
How far away would the Andromeda galaxy be on this scale? This is our scale factor. Does that help you?
Yes, it does. So
All right.
we can go to centimeters prime.
Because that's the whole point of a scale factor is we invented our own conversion factor. See, I think you were worried, oh wait, do I have to go to kilometers? Do I have to go to meters?
Yeah.
We've created a scale factor directly from light years to fake centimeters. Remember, we're trying to get the scale model centimeters. So we're converting from light years to fake centimeters. All right, and now step 4, Sage.
We're going to put 100,000 on the bottom and 1 centimeter on the top.
Right, we keep the 100,000 with the light years. So they go on the bottom. And 1 on the top. Okay. Punch them up, or 10 to the 6 divided by 10 to the 5. What should we end up with there? Light years cancel out. Anyone?
25.
Yeah.
25 fake centimeters. Okay, now we're going to have to make a line. By the way, the Ryans know this, but Sage and other new friends, every time I do one of these problems, when I grade them historically, each problem, so that you know, is graded out of 5 points. Each homework is graded out of a total of 25 points. So that you can understand how I do business, every time I do a problem, I pre-assign in my mind what each of the points are worth. Doing this conversion with dimensional analysis has earned us 1 out of our 5 points. Drawing the proper scale in part A will earn us 2 more points. So that if you make that actually 1 centimeter, that's another point. Now we have to draw a line that's 25 centimeters. This is probably going to take the whole diagonal of your page. So you'll have to draw a line that's like 25. Make it diagonal, just like you see me doing. All the way down through the page. And then at the bottom of the page, you will have another 1 centimeter line. and you put another galaxy to represent Andromeda, okay? And we can even label this, if it's not too messy, 25 centimeters. This should also be 1 centimeter. I use slightly different values because I have to present it to you on the board. And so that's part A.
This is going into inches. I'm just using half an inch for a centimeter. Is that okay?
A half an inch is like almost 2 centimeters. Wait, hold on. No, I'm sorry.
Okay.
That's close enough. Okay, sure. I don't think by eye I'll notice it. Boy, that's some, low-tech solution there. I guess, is that all you had was a tape measure, Sage? So wait,
Yeah, I was like running around asking my roommates, but
Guys,
I'm just gonna get
if
one
ever there was
tomorrow,
a
yeah.
symbol of if ever there was a symbol of a mathematician, that's it. Their whole lives are numbers, and yet they don't have a single numerical measurement device like this. Doesn't that just okay, but doesn't that just, it's in inches, doesn't that just sum it up? The difference between science versus math is that the scientist actually does something with the numbers. Okay, that's fine, Sage. We'll accept it. All right. Ryan Dick, part B.
How does the separation between galaxies compare to the separation between stars?
All right.
Based on your
Well, wait, I'm sorry, Ryan. I'm sorry to interrupt, but there's two parts to this question, and I want to just deal with them differently. So let's just take your first statements there. How does the separation between galaxies compare to the separation between stars? Now, what's the closest star to Earth? I'm sorry, the closest star to Earth is the sun. I always fall for that one. I hate when astronomers do that. What's the closest star to the sun?
I have no idea.
Really? No sci-fi fans out there?
Isn't it Alpha Centauri?
Alpha Centauri, Ryan Spavel, yes. Do you remember how far away Alpha Centauri is?
Isn't it like 2.5 light years or something like that?
4.4 light years.
4.4, okay.
It's a big, I don't know. If you're a sci-fi nerd like me, Alpha Centauri shows up in science fiction books all the time. 4.4 light years to Alpha Centauri. So let's say that the Sun and Alpha Centauri, let's assume that they're typical, ordinary garden variety stars. Typically, stars are separated by 4.4 light years. Let's also assume that the Milky Way and the Andromeda Galaxy are typical garden variety galaxies. Then typically galaxies are separated by 2.5 million light years. So how does the separation between galaxies compare to the separation between stars? How would you describe that? Not looking for, no tricks here, guys, just no tricks. What do you think we should write for the first answer to that first question in part B? I don't understand. Is this a hard question?
Oh, it's much larger. I was just rereading the question.
What is
sorry.
it?
The distance between galaxies is much larger than the distance.
Let's be quantitative of it. Here's an old astronomy trick, Sage. Pretend 4.4 equals 2.5. If you did that, we could just say to an order of magnitude, look at the math guy, 4.4 equals 2.5. I'm going to ask you to think about that, okay? You could literally say that if 4.4 equals 2.5 and they cancel out, that the separation between because to an astronomer, that's true, by the way. 4.4 does equal 2.5. You know why? because who fucking cares?
Yeah, because you're
It's
dealing
a
with
factor
complex
of order
numbers.
2 to 4 or whatever, right? So we could literally say that galaxies are writ large millions of times farther apart than stars, right? Let's start by writing that down. The separation, please, I never spell separation correctly, so keep me on my toes, guys. The separation between galaxies is millions of times greater than the separation between stars. Okay, Ryan, Dick, I had to interrupt you because part B has 2 parts, and this part is the easy part. The second part we have to talk about for a minute. So Ryan, read us the rest of part B if you're willing.
Based on your answer, discuss the likelihood of galactic collisions in comparison to the likelihood of stellar collisions.
In other words, what that's saying is what's more likely to collide, stars or galaxies? Now, most of you guys were there with me on Tuesday. What did we learn? You
That
remember the
stars
so-
almost never collide while galaxies will often collide. No,
So
Oh,
how am
no.
I supposed to justify that when we just said that the separation between galaxies is millions of times greater than the separation between stars?
would it have to be in terms of diameter? Because on a much larger scale, a galaxy is on for the Milky Way and Andromeda, it's 100,000 light years, while a star is only like probably around 64 kilometers,
Yep.
1,000 kilometers.
The diameter of the sun is 1.5 million kilometers.
Oh,
So actually,
Okay, so
first of
way
all,
off,
let me
but-
just say that yes, Ryan Spaveld, that was the correct answer. It's not just about the distance, it's also about the diameter of the objects as well. In fact, Ryan, what I'm going to suggest that we say is connect the two and we talk about distance to diameter ratio. Now, because you guys are good and because you guys are trained, I want to ask you guys a question here. Why didn't they ask us to do part A for stars? Isn't that weird that they asked us to do it for galaxies, but not stars? Let's play a quick little game here. I hope you guys have gotten all that down. Let's imagine they'd asked us to do part A for stars. In that case, the sun would be a sphere. The actual diameter of the sun, if we're being careful, is 1.4 million kilometers. And then Alpha Centauri is 4.4 light years away. What if they had asked us to do part A for stars and come up with a scale factor in which 1 centimeter was equal to the diameter of the sun? Sage, because you're good and we can do this quickly, why don't you help me convert 4.4 light years to fake centimeters using dimensional analysis? And I'll start you off. We start with the number that we want to convert with its units.
For sure.
Then we make a division bar. Give me some units.
We're gonna throw 100,000 light years.
Whoa. Did you just try to bust out some numbers? You do not have permission to do that.
Oh,
In
I'm sorry.
dimensional analysis,
I'm sorry.
units first.
Yep. So light years on the bottom and centimeters prime on the top.
Nah. That was for
Nope,
part
nope.
A.
So
We
what?
have a new scale factor now. Our scale factor for stars is 1 fake centimeter is 1.4 million kilometers. This is a new scale factor. You can no longer go from light years to fake centimeters because now we're making the sun 1 centimeter. So
Yeah.
try again.
So let's throw kilometers on the top.
There we go. And then what will we do in our next division bar?
Kilometers on the bottom and centimeters per on the top.
Fake centimeters, right. Okay, now I know you love the numbers. Help me put them in, okay?
Let's throw 1.4 times 10 to the 6 kilometers on the top to 1 light year on the bottom. And
Whoa,
no, actually, yeah,
Wow.
no.
That was last night's whiskey talking right there. I just want to.
Yeah, I'm sorry. I actually don't know that conversion factor off the top of my
It's in
head.
your. Did you take notes last time? By
I
the way,
did.
I want to say, guys, that you're going to hear me pick on Sage from time to time, but I think it's great that there's a hip, young, cool person who's into math and wants to do math as a major. That's awesome, Sage. And
started
I
with
love
video
it.
game programming, but coding sucks. So
Well, I'll tell you this, Sage. When it comes to coding and stuff, when I was in college, I really hated all of my coding classes, and because you have to do a bit of that in physics and astronomy too. And I was really bad at it, and it was like pulling teeth. I hated it. Once I got out of college and I was in the real world, coding is really fun because you're kind of lost in your little matrix cube at work, and no one really knows what you're doing, and they can't understand it. And each day it was like going to work and solving a little mind puzzle. So you'll actually find that when you're getting paid shitloads of money for it, that it somehow starts to be a lot more fun. So
that was the pull. I just hate debugging.
Yeah. But remember, you got to think about it like a little puzzle. You invented a little brain damaged baby, and now you're trying to figure out how to fix his brain damage and make him work.
Recut these pieces. Yeah.
Anyways, having a math major in the class is nice because it highlights differences between math and science for students. So that's what I'm taking. Anyway,
there's a lot. Yeah.
Go ahead and get me that conversion factor.
I believe it's 9.5 times 10 to the second or 10 to the 12th kilometers over 1 light year.
Yep.
Okay, cool.
And then what we use.
And then that weird one. Yeah, the 1.4 times 10 to the 6th from the bottom and 1 on the top.
Okay. So can you guys punch that up for me? Tell me what you get. I'm making this problem a little longer than it needs to be, but that's okay because it makes it cool. For the benefit of people watching later, are there any people watching later? I don't know. Here's how you would do that. We're going to do this times this and then divide by that because we don't have to pay attention to the ones. So I would do 4.4 times 9.5. Remember, we use the EXP key, EXP12, and then we divide by 1.4 EXP6. Is that what you got?
Mm-hmm.
Sage or either Ryan's, what would be a tasteful way to express this number? Help me express this number in good taste, because I certainly don't want to see that on the page. Be
That would
bold.
be 2.9 times 10 to the 7th.
That is correct, Ryan, but make it even more elegant for me.
Okay, 29 times 10 to the 6th.
29 million, or let me make it even more elegant than that, Ryan. Let's say it's approximately 30 million fake centimeters. Oh! The reason they didn't ask you to do part A is because your page would have to be 30 million centimeters. Wait, could we convert that to like kilometers? How could I convert that to kilometers? First, I would go from fake centimeters to what? To fake meters, right? And then I would go from fake meters to fake kilometers. Can you guys give me the conversion factors for those? Anyone?
1 meter to 100 centimeters and 1,000 kilometers to 1 meter.
1,000 kilometers?
Or 1,000 miles, or flip it.
1,000 meters, 1 kilometer. In other words, this is 10 to the power of 5. So your paper would need to be 300 kilometers long. What's the width of, is that like the size of Connecticut? Wait, if Rhode Island is 80 kilometers long, that's 3 times the length of Rhode Island. I mean,
Maybe New Jersey the long way?
yeah. I was just thinking, you know, every time I drive to New York City, it's those 93 exits of pure hell in Connecticut. So I was wondering if maybe that would be, could that be 300 kilometers? It's kind of cool. What's the length? Oh, wow. Oh, sorry, the width is only 200 kilometers. So that'd be even longer than Connecticut. That's why they didn't ask you. That's why they did not ask you to do part A for stars. So once again, Ryan Spaveld already had the right answer. Let's see if we can sum this up a different way. And this is something I'd like you to put on the page here. If we consider the distance to diameter ratio for galaxies, the distance to diameter ratio is 25 to 1. But for stars, the distance to diameter ratio is 30 million to 1. See what I'm saying? Let's play that game again, Sage. Let's pretend 25 is equal to 30. In that case, stars are millions of times further separated in comparison to their diameters, right? So let's add this last sentence to part B, and then we'll be done with this problem. However, the distance to diameter ratio for stars is literally millions of times greater than galaxies. Thus, stars almost never collide, but galaxies do. Sorry, that was poor form there. I ran out of space. Stars never collide, but galaxies do. You guys get all that on your page there? Sage and Ryan's, let me know when you're done with a thumbs up or something. Cool. All right. Guys, I'll try not to drag the rest of the problems out like that, but that problem required, in my opinion, a little extra TLC to make it good. I'm going to erase now, okay? We'll try to move faster going forward here. Okay, Ryan Spavels, do you want to do 49?
All right.
Let's label this properly, chapter 1.49.
49. Universal scale. Suppose we wanted to make a scale model of the local group of galaxies in which the Milky Way galaxy was the size of a marble, about 1 centimeter in diameter. A, how far from the Milky Way galaxy would the Andromeda galaxy be on this scale? And B, how far would the Sun be from Alpha Centauri on this scale? C, how far would it be from the Milky Way galaxy to the most distant galaxies in the observable universe on the scale?
Stop me if you think you've heard this one before, but I think we just did sort of this problem. That's okay. This is just going to be a straight up dimensional analysis problem. So let's do part A, okay? So from part A, we already know that Milky Way to Andromeda is a distance of 2.5 million light years, right? So let's do our dimensional analysis just like we did in the first part. Ryan Spavold, walk us through it. I've got a division bar, units, top and bottom.
That would be light year on the bottom and centimeter on top.
Conversion factor.
1 centimeter on top and 100,000 light years on bottom.
Yeah. And we already know what the answer is going to be, right? Right? Anyone?
It's 25 centimeters.
Yeah. Let's put a box around it because that's a classy move. Part B. Part B is the Sun to Alpha Centauri. Distance 4.4 light years. I'd like to point out that this is different than the previous problem. Sage, in the previous problem, we scaled the Sun to 1 fake centimeter. In this problem, they're allowing us to keep the same conversion factor, right? Okay, so I guess Ryan, Dick, would you be willing to walk us through this one?
Yeah.
Should be pretty straightforward. What, same thing, right? What do I do?
You add the division bar, or yep. Light years on bottom and centimeters on top.
Take centimeters on top.
1 centimeter on, or 1 on top and 100,000 on the bottom.
Yep. And then punch that up and tell me what you get.
Uh, 4,400.
No. It's got to be less than 1, right? 4 divided by 100,000 is going to be a small number.
Yeah, I'm a dummy. I accidentally multiplied it.
Oh, this is important for people at home too. You're multiplying, but you're multiplying by 1 over 100,000. Essentially, what you're doing is this divided by that. If it's on the bottom, you
Yeah.
have to hit divide. Okay. That might be an issue for people watching at home. Hey, you people at home, I know you're not punching it into your calculator. I know you're just watching, and you are going to pay for that, okay?
4.4 times 10 to the negative fifth.
Right.
Is this something you would want to change into a sig, or would you, since it's a decimal, would you want to keep it that way? Just for
I'm sorry,
formatting purposes.
Can you rephrase that, Sage? I didn't understand.
Yeah, do you want that to like 44 times 10 to the negative 6 for formatting purposes, or would you rather leave it there because it's a decimal?
Yeah, I think I would just leave it there. There could be an argument to be made to saying 44 millionths of a centimeter. That kind of could be
Yeah.
classy.
I
know-
was just
For some reason, I
wondering if
never
there
think
were
to
rules.
do that. Tiny numbers bamboozle people. Negative powers bamboozle people.
Yeah,
I could almost, if it was just you and me, Sage, I'd say nice. But
yeah.
I
Just
think
for my own
I think there's
note-taking,
people out there at home who are even just struggling with scientific notation.
Absolutely, yeah.
So, we want to keep these in By the way, it is rather difficult, this homework session. I only have 3 people to work with. One of them is a math major, and the other 2 have trained with me. So that's kind of cool because we can blast through the homework. But I'm worried that with people at home, there will be people that aren't really well trained in math, and seeing us just kind of gracefully tiptoe through this, it makes it look too easy and it could be scary. It almost helps to have a mix of people who are good and bad at math in the class, just so that we can pace it appropriately. I really don't know what to do about that because you guys cannot unlearn what you have learned, nor can I. So I'm just gonna crank it up and go. And hopefully the people at home will be following as best they can. But if you're in the background there and you are confused, the doctor is always on call. So you could call me later on tonight and ask me some questions if you want to. I'll take a call about homework stuff, right? All right, let's do part C. Now here's where I can be of help. They're asking about the distance to the edge of the observable universe. You guys might know this, but I suspect that because you haven't had a galaxy type class with me, you might be not aware about that. But the universe has a finite age. The best estimate is set by studying the cosmic microwave background. That's kind of a long story, so I don't want to get into that, but I think the Planck satellite sets that. If I type into Google age of the universe, I want you to take a look at the precision on this. So based on observations and an assumed model, look at this. Look at the precision on this age. 13.772 plus or minus 0.04 billion years. People are arguing about the 4th significant figure on the age of the universe, meaning everyone's agreement
I'm
that
not
it's,
gonna lie.
huh?
I love that. I'm not gonna lie.
I love that too. I think that's so cool. Everyone's on board with it being at least 13.8, but it's this digit that they're arguing about. So we actually have high precision measurements that allow us to estimate the age of the universe. Now, light takes a finite travel time. So if there's a finite travel time to light, light can only have traveled 13.8 billion light years since the beginning of the universe. And that means if we look out in any direction, it doesn't actually matter how big the universe really is. We can only see a 13.8 billion light year radius of it in any direction. Each day it grows a bit as light can travel farther, but there's a limit to how far we can see based on time and the speed of light. So the edge of the observable universe we could say is 13.8. How many zeros are in a billion?
That's gonna be 9.
9 light years. And that's what we'll convert into fake centimeters. So 13.8 billion light years. By now, you guys should know the drill. Light years in the bottom, fake centimeters in the top. 1 to 100,000. And 9 minus 10 to the 5 is 4. So that's 138,000 centimeters. On a scale in which our galaxy was a centimeter in diameter, the observable universe would be 138,000 centimeters, and I think that's 1.4 kilometers. That's the edge of the observable universe. Okay. Forgive my yawn. Astronomers stay up all night. That's what they say, all right? There we go. Let's see if we can crank out these next 3. I need to warn the studio audience. In our first lecture, I spent a lot of time going over the rules of the road, scientific notation, and dimensional analysis. And that's kind of all I really did, plus a couple of vocabulary words. I think the next three problems are all about angles. And I really should start off today's lecture with angles, but we're going to kind of munch through these problems anyways. What I should do, I'm going to erase here. Can I erase this, guys? Ryan, Dick, are you okay?
Yeah.
All right. In today's lecture, I will give us proper notes on angular size and angles. But for now, before we do our next problem, let's just do a quick, microscopic crash course. There are three different units for angle that we're going to use in this class, okay? The symbol that we use for angles is the Greek letter theta. You don't have to speak Greek. It just looks like a zero with a line through it. There are degrees, right? The rule for degrees is one circle contains 360 degrees. I'm guessing you've heard of degrees before. Even the most basic math users heard of degrees. Astronomers use two smaller angles that some people have not heard about before. Arc minutes and arc seconds. I'm going to go over these things slowly and carefully during lecture today. But for now, all you really need to know about arc minutes and arc seconds is that the symbol for one arc minute is 1 with an apostrophe. The symbol for one arc second is 1 with a double apostrophe. And the rule is 1 degree contains 60 arc minutes and 1 arc minute contains 60 arc seconds. And we can treat these as just conversion factors, and we can use dimensional analysis. But if anyone cares to understand, an arc minute is a really tiny angle that's a 60th of a degree. An arc second is an even tinier angle that's a 60th of an arc minute. Okay? I've got a lot more to say about that, especially in an astronomy context. But since that's a part of today's lecture, I'll just wait for there, and let's just see if we can solve these problems. So, Sage, can you read us chapter 2, number 53?
All right, arc minutes and arc seconds.
Sage, can you pause for 1 sec? I just need to get water. Sorry about that, Sage. I thought I could make it through the next problem without water, and then I realized, nope, no, I can't.
No worries whatsoever.
So hit me again.
So arc minutes and arc seconds. There are 360 degrees in a full circle. Part A, how many arc minutes are in a full circle? Part B,
All right, let's just do one at a time because we'll forget. So they want to know arc minutes in one circle. This is going to be an easy problem for all three of you. Sage, I'm going to ask you to do it just because I know the two Ryans have trained with me on arc minutes and arc seconds before. Okay, so let's do it dimensional analysis style, Sage.
Absolutely. So we're going to start with our 360 degrees.
Sure. Actually, we could even start with one circle, which would have been cute too, but let's start with 360 degrees. But that's how one person in the 1010 class yesterday started with one circle. So we did the dimensional analysis, and that was kind of cute. But
hey, I mean, that is another unit.
Indeed, right?
Yeah.
One of the things you will learn is that you can get quite creative with units. Anything can be a unit. You can even make them up if you do it cleverly.
As long as we're not doing derivatives with them, I'll be happy.
Is that where, are you currently in calculus or?
Oh, so my old school that I went to had an upside down curriculum. So I've already taken all of my math classes. I transferred with like 36 credits. So now I just need all my extracurriculars and history and labs. And so I'm actually really happy we're doing math in this lab because I didn't think I'd get to do math until I went to go get my bachelor's. But
Wow. That's
Yeah.
very interesting. So, but I was wondering, like, so I, as a physics student, I had to do Calc 1, Calc 2, Calc 3, Calc 4. Calc
Mhm.
4 is differential equations. I don't know if you would. We can talk
Yeah.
about it offline. I don't want to bore the audience here. Anyways, let's
got
just
you.
let's do this problem.
So let me just catch up a little bit. 360 degrees, and we're going towards arc minutes. So we're gonna put degrees on the bottom.
Yeah.
And we're gonna put arc minutes on the top. And we're going to put 1 on the bottom to 60 on the top.
Okay. And someone
And-
close that up. Give Sage a chance to catch up. One of the Ryans, give me the answer there. Because Sage probably needs to write some stuff down.
It is 21,600 or minutes.
Nice. Okay. In part B, they ask for the number of arc seconds in one circle. How do we want to start this one, Sage?
So we could actually start with 21,600 arc minutes.
Right,
Since we
we
just
already
did that
did that.
conversion.
Okay. Now we
And
use
then-
step 2, which is the division bar.
It's going to be the arc minutes on the bottom and the arc seconds on the top. And it's actually the same conversion factor in terms of numbers, but not in terms of units.
Okay. And someone punch that up for me. I got it. I'm so sorry.
Poly MS.
I ate really spicy Indian food for breakfast, and it just came up and attacked me out of nowhere. God. Sorry, everyone. Yeah, wouldn't that, what if I just keeled over?
I wouldn't know who to call.
Sorry, what's the answer?
Let's do 1.3 times 10 to the
Sage, I want to have a level 2 discussion with you here. Level 2.
Yes.
We don't need to round here. Do you know why? Let's talk about precision and measurement. I don't need to round. The actual number that I believe you got, and he did right to put it into scientific notation, but let's do it without scientific notation for a second.
Okay.
You actually should have gotten 1,296,000 arc seconds, right?
Yeah.
That all of those sig figs are valid. Why?
I thought the first conversion factor had 3.
If you just looked at it like that, like numbers, but what about this? That only has 1 sig fig. Aren't you
Yeah.
supposed-
Oh,
you
so
supposed-
you'd use the lowest. So
You're missing the
yeah,
point.
so yeah, entirely missing.
Let me explain it to you in terms of a basic geometry thing. You know from basic math that the radius of a circle is half the diameter, correct? If I say the radius of a circle is 1/2 the diameter, that 1/2 is not a measurement, it's a conceptual ideal. By design, by conceptual ideal, the radius is exactly half with infinite precision.
Okay. So
Conceptually,
these are all conceptions.
they are, and they
Yeah.
have infinite precision because
Okay.
we define that there are precisely, exactly a perfect 360 degrees in one circle.
And that's a
We-
law, not a theory. Okay.
Well, it's just, no, it's a,
Just in terms of
it's a, I want to find some cool math term. It's a proposition. It's an axiom It's something that you're starting.
Hey.
It's an axiom, okay?
Yeah.
I think I used that word correct. I don't know. Anyways, we're saying that by design, in fact, in math, they often use a triple equal sign to say defined as such.
Okay.
Because of that, there are exactly 1,296,000 arc seconds in one circle. That's just a cool point to bring up. Be careful. Precision comes in when there are measurements, right?
Yeah.
When there are measurements.
There was nothing measured here.
Exactly. Okay.
Yeah.
Now let's do part C. The moon. The angular size of the moon, and I'm going to have to explain this later on, is 0.5 degrees on your sky. That's roughly half the width of your finger outstretched. Our job in part C is to convert that both to arc minutes and to arc seconds. Let's make light work of that. So 0.5 degrees times the division bar, units.
Degrees and arc seconds. Degrees on the bottom and arc seconds on the side.
Wait, no, they want arc minutes first. Part C has two parts.
That one.
Arc minutes on top. Degrees cancel out. What's my conversion factor?
60 and 1, which leads you to 30.
Yep. $30 arc minutes. And now we have to convert that to arc seconds. 30 arc minutes times the division bar, arc minutes on the bottom, arc seconds on top. Cancel out the arc minutes. The conversion factor is 60 to 1. And what's that give me?
1800.
Arc seconds. And that takes care of our third problem. Nice. I should also say before we do our final two problems, we're doing okay on time here. If it continues to be just the three of you guys, I'm still willing to do live lectures, but we might want to actually think about using some of the pre-recorded homeworks. One reason is that you guys are all pretty well trained. And I think it will help some of the students watching at the studio audience to see some of my recordings with the other classes. They're paced at a rate that's maybe better for those other students. I haven't really fully made up my mind yet. I did put a limit of 5 people sharing video, but I'm willing to do live lectures for 3 if you guys really want them. We might think about next week farming out the homeworks. It depends, you know. It'd be nice to give myself a little breathing room, but what I'm especially worried about and what I can see happening is when I'm working with the 3 of you, I'm not explaining some things that I think you already know. So I'm worried that I'm going to go too quickly, you know. So these are just thoughts that I'm having in my head. We'll see how that goes. It might be that I ask the class to watch the homework maybe beforehand or whatever, and then we'll just do lecture and lab as a live thing. You guys can let me know your thoughts about that. I'm open-minded to a bunch of different ideas. I was kind of hoping that as we did this, more people would see the benefit of it, of trying to join live. But I think the time slot that I scheduled things for during the day for me might actually be hard for students who work during the day, you know? I don't know. Those are just thoughts that I'm having. All right, let's go on to 55. I'm going to erase. Do you guys have all this? Okay. So chapter 2, number 55. I don't know, anyone who's got, who wants to read that?
I can read it.
Thanks, Ryan.
Angular conversions 1. The following angles are given in degrees and fractions of degrees. Rewrite them in degrees, arc minutes, and arc seconds.
Okay. Hold on. Before you start with that, Ryan, this is something that you guys might not understand. We didn't do a problem like this in 1010. Today, you're going to be learning about stellar coordinates, which is kind of interesting, kind of cool. Let's go ahead and look up a favorite star. A star that I've been looking at in the sky lately is the star Arcturus in Boötes. I want to show you something. If we go to the Wikipedia page for Arcturus, they list the coordinates of the star. You're going to be learning about these coordinates today. They're kind of like latitude and longitude for the sky. They're called declination and right ascension. But I want you guys to look at the right ascension is kind of nutty, so we're going to get to that later. But I want you guys to look at how they format the declination in degrees. And this is something they do also for latitude and longitude on Earth. Positive 19 degrees, 10 arc minutes, and 56 arc seconds. And you'll see that that's quite common, is to break it into degrees, arc minutes, and arc seconds. Let's go ahead quickly, and I'll show you this in our lecture today. If you are using an iPhone and you go to your compass app, so I've got a little compass app here, and let me do the focus. You can see that I will get my latitude and longitude. I think I want to go to around 50 or so. Over here. You can see that in my compass app, they've printed, where's the best focus? Whoa, hey, no. Oh, there we go. They're giving you my position on Earth also in terms of degrees, arc minutes, and arc seconds. So that's kind of a common formatting thing to do. So what they're going to do in this problem is they're going to give us a decimal number of degrees, and it's our job to convert it to this format. Let's start by writing this down. The format that we want to convert to is some number of degrees, some number of arc minutes, and some number of arc seconds. All right, now Ryan, Dick, you can read us A.
24.3 degrees.
All right. So what do you guys think we should do here? How do we go about this?
Dimensional analysis?
Kind of, yeah, but there's with a little twist here. What do you want to do dimensional analysis on?
I was thinking maybe take the conversion factors and just plug the 24.3 degrees in it.
That's not going to work.
No.
Does anyone see why? We need to format this into a whole number of degrees, a whole number of arc minutes. The arc seconds do not have to be whole. They can have a decimal. You know what I mean by whole, right? Like a...
Yeah.
We already know the whole number of degrees. What's this one going to be?
24?
Exactly. So we already have, let's do our format, okay? We already have 24 degrees. What we need are the arc minutes and arc seconds. So we don't want to do dimensional analysis on 24.3 degrees, Ryan. We want to do dimensional analysis on...
24 degrees.
Nope. Someone figure this out. I don't want to have to, yeah, Sage?
Yeah, you're gonna do it on the 0.3 because the
That's the stuff
arc minutes and arc seconds are the in between.
they're the smaller versions, right? So we're
Yeah.
taking the remainder, the change, and we're converting the change into different units. So in fact, it's the remainder, it's the 0.3 degrees that we wish to do dimensional analysis on. Oops. Oh, whoa. Check out my student maneuvers there. Look at that. That doesn't work. Guys, give me the units top and bottom.
Degrees on the bottom, arc minutes on the top.
Yeah. We got to make sure that we cancel out degrees on top and degrees on bottom. And what's my conversion factor?
$60 on top, 1 on bottom.
Right. And so what does that give us?
$18.
Did you say 18,
arc
Ryan?
minutes.
You're a little quiet, Ryan.
Oh, I am?
Yeah. I would like you a little louder, but I'm also deaf, you know, so. Or rather, I damaged my hearing with loud music. That's what I meant by that. What are we going to do about the arc seconds?
Would it just be 0 because there's no remainder?
Exactly. Let's use cell padding. That's what they call this, cell padding. And let's make it a double 0. Sometimes cell padding can be useful to maintain a similar format. Okay. B, Ryan.
1.59 degrees.
Okay, so you guys are starting to get this, I think. We can see that we're going to have 1 whole degree. The trick is to get the arc minutes and the arc seconds. Tell me what to do. Guide me.
You put 0.59 degrees
Yep,
and multiply it by the division bar,
yep,
and then you put degrees on bottom and arc minutes on top.
yep.
60 on top, 1 on the bottom.
Good. And what's that give us?
$35.4
Units?
arc minutes.
How do we proceed from here, Ryan Dick?
You put the 35 in the arc minutes slot and put the 0.4 to multiply by the division bar.
We're going to convert the remainder of arc minutes into arc seconds.
Yep.
Units?
Arc minutes on the bottom and arc seconds on top.
Okay. Conversion?
60 on top and 1 on bottom.
6 times 4 is
24.
the 0.4 kills the 0. 24 arc seconds. Okay, let's speed it up for the sake of fun. Part C.
Uh, 0.1.
Degrees. So we have double 0 degrees. Just get my format boxes set up. 0.1 degrees. Degrees to arc minutes, 60 to 1. What's that give us?
6.
So we have 0, 6, 0, 0. Right?
Yep.
Okay. Let me know if I'm going too fast here. I'm going to erase this stuff. D.
Uh, 0.01.
Okay. Once again, we have 00 degrees. 0.01 degrees. Degrees on bottom, arc minutes on top. 60 to 1. I think 6 times 1 is 6. There's 0.01 to 60. If you punch it into your calculator, I think that's going to be 0.6 arc minutes, correct?
Yep.
And what do I put in for my second box?
0, 0,
Yeah.
0.
Yep. And now we have to do the remainder, 0.6 arc minutes. Arc minutes on bottom, arc seconds on top. 60 to 1. 6 times 6 is 36. The 10 kills the point. I don't know if that made any sense to you. I was thinking garbled thoughts in my head. Okay. And now lastly, we have D. Sorry. Lastly, we
E.
have E.
0.001.
Okay. So we already know we're going to get 00 degrees and 00 arc minutes, because this number is 10 times bigger, right? In fact, I bet you guys could even guess. What are you going to get for your arc seconds? This number is 1/10 of that number.
Probably 3.6.
Yeah.
Yeah.
Let's confirm it. Let's do 0.001 degrees. Let's see if we can do a two-step dimensional analysis. Degrees cancel into arc minutes. Arc minutes cancel into arc seconds. 60 to 1, 60 to 1. 3,600 times 1,000 is exactly what we suspected, 3.6 arc seconds. Confirm that with your calculator if you're bad at math. Not that I'm particularly good at multiplying and dividing numbers, but I like to practice when possible. One last one to go. How are we doing on time? Oh, we still have almost a half an hour. Oh, I gotta, my clock on my computer says 11:28. My iPhone says 11:36. I need to fix that. Something is wrong. I don't know why I'm having trouble updating.
That's confusing because I thought they would all be synced to the same clock.
Yeah, and I figured out how to do this the other day.
Maybe your ticks are off.
Huh?
Maybe your ticks are off. I don't know. But that'd be, I don't understand.
I think the phone is correct. What does your computer clock say? Does your computer clock match your iPhone?
Yeah, they're 11:37.
Wow. Why does all right, that's not a problem for now, but I could have figured that out. It's confusing because I'm running the show and I'm sometimes using that clock as a reference, but it's behind. So let's do number 58. In number 58, we're going to be making use of a formula that unfortunately we didn't quite get to in our lecture last time, but I will pretty much be starting today's lecture on it. The name of the formula is called the small angle formula. And the reason why astronomy students need to learn this formula is you need to know this formula to even understand how an astronomer thinks about the sky. And the basic picture that we have that I'll be showing you in our lecture today is when you look at astronomical objects in the sky, whether they be stars or galaxies, whether they be planets or moons, you need to understand that we see things in terms of angles, not in terms of sizes. For instance, here in my room, I have Moonball, and Moonball has a true physical diameter. I lost that clear plastic ruler. Oh, here we go. If I were to do it in centimeters, you can see that the physical diameter, well, it'd be nicer if we had a focus here, but just for illustration. Oh, shoot, did I close that Logitech? I did. That was dumb of me. Okay, I need the Logitech app to focus because this camera is stupid. What did you get? Did you get a Logitech, Ryan?
I got Depths Tech. Depths Tech. I just grabbed the first one on Amazon.
Yeah, can you adjust? So for this one to adjust the focus, I need to go into their app. It's just irritating. Anyways, I'm just complaining for fun.
Yeah, mine was fine just right out of the box.
There was also a technology grant from CCRI that was giving away free laptops. That's how I got mine. I don't know if everyone knew
Yeah,
about that. I
the
didn't
problem
get
is
it.
my internal laptop camera, the that I got from CCRI, the camera wasn't quite good enough. Since I have to produce these videos, I needed something of a higher quality. So you can see that Moonball is about maybe about 6 centimeters in diameter. This ball might be 6 centimeters in diameter, but you don't see 6 centimeters. You see an angle. And this represents some number of degrees in your field of vision. Actually, the webcam works on the same principle as your eye. If I bring Moonball close to the webcam, it takes up its entire field of view. Your field of view is really close to half a circle, 180 degrees. You can even see when you wiggle your fingers in peripheral vision. It's not quite 180 degrees, but it's close to it. As I move Moonball away, Moonball appears smaller and smaller. And that's because the camera also sees Moonball as an angle, okay? So the fundamental problem that the small angle formula is relating is something like this. We have a star or a moon, like so, and I want you to draw this on your homeworks. The star or the moon has a diameter, which we will call S. S could stand for the physical size or the diameter. And for starters, we're going to probably try to measure that in kilometers. You're observing that star from somewhere far away, presumably on Earth. Unless you're Neil Armstrong, you're going to be looking at this thing from Earth. And let's put an eyeball over here to represent the fact that this is where the observer is located. And that star or moon is some distance away. In astronomy, we tend to use little d for distance. And I kind of know why that is, but I don't want to get into it. Little d represents the distance. And for now, we'll keep things simple. We usually want the distance to be measured in kilometers, for starters. And the angular size, we're going to once again use that letter theta, which is like a 0 with a line through it. And theta will represent the so-called angular size measured in degrees. And that's, for our formula here, going to be a necessity. These three quantities, the diameter of the star, the distance to the star, and its angular size, are related to each other by the small angle formula, which looks like this. The size of the star is the angular size times the distance times 2 times pi over 360 degrees. Now, I think you all know about pi, but it could be that someone watching this video later doesn't know about pi. Let's find out how much Sage knows about pi. Tell me some things about pi, Sage.
Sokotoa. Pi is a non-repeating decimal that goes on.
Do they call it an
infinitely.
irrational number?
It is an irrational number, yeah.
Okay. How many decimal places do you know it to?
3.141592. That's it.
I've got 3.14159265354. I have
I
as
thought it
many
was a
as
6, but
I have as many as appears in the Casio because I'm used to looking at it. Now, I want to show you guys some. By the way, not to put you too much on the spot, Sage, but where does pi come from?
oh, I actually don't remember. I just used it a lot.
Well, I will tell you where pi comes from, Sage. Greek geometricians, they discovered, because they loved circles and they loved geometry, they discovered that every time they made a circle, no matter how big or how small, if they took a length of string and laid it along the circumference of the circle to measure its circumference, and they measured it, and then they compared it to the diameter, that the circumference of a circle was always bigger than its diameter by a number that had no end and was only limited by the precision to which they could measure the circumference and the diameter. In other words, they discovered that the circumference of a circle divided by its diameter, the ratio, was always that magical number, pi, 3.141. And in fact, you can see that definition in the formula for the circumference of a circle. It's 2 pi r, right? And there you see the definition of pi, because 2 times the radius is the diameter. The circumference is pi times the diameter. So pi comes from just the fact that basically the way I think about pi, I think of pi as a conversion factor that converts from linear dimension into circular dimension. And anytime there are circles, pi shows up. And because astronomy is basically the science of circles, pi is everywhere. Now, pi can be found on your calculator, and here I want to introduce people to some Casio functions, especially for those who aren't so good with this kind of jazz. In the Casio calculator, you can hit the buttons, but there are orange buttons that can only be activated by hitting Shift. For instance, if I wanted to take the square root of 9, I would have to first hit Shift and then square root of 9. The pi button is located above our EXP key, but do you guys notice how it's in gray? That means something sneaky. I can hit Shift EXP, and I will always get pi, 3.1415926. I think it's 5354, but they rounded. Anyways, however, here's the tricky part. Because pi needs to be accessed a lot in math classes, you can just hit EXP by itself and get pi. But that makes EXP a kind of dangerous key. Watch this, guys. If I do 2 times EXP, that's 2 times pi, right? But if I don't hit the times, it works like a scientific notation key. 2 EXP3 is 2000. The 2 Ryans probably already figured this out intuitively, but other students for the first time might want to be careful, okay? All right, just wanted to say there is a pi key on your calculator. Now we're ready to read the problem. Sage, go ahead and read it to us. 58.
This is number 58. Let's see. Oh, I do not know that first word. Betelgeuse.
Betelgeuse.
Oh,
Betelgeuse.
okay. Betelgeuse diameter. Estimate the diameter of the supergiant star Betelgeuse from its angular diameter of 0.05 arcsecond and distance of about 600 light years. Compare your answer to the size of our sun and the Earth-Sun distance.
Okay. They've given us the angular size as 0.05 arcseconds, and the distance away is 600 light years. Our job is to calculate the diameter of Betelgeuse. In the interest of time, I want to just point out the trick in this problem. Our formula requires the distance to be in kilometers. Well, it doesn't really, but I'm going to lie to you because it's easier. Our formula requires the distance to be in kilometers. Our formula requires the size to be in kilometers. And our formula requires the angle to be in degrees. They gave us the angular size in arc seconds, and they gave us the distance in light years. So what we need to do are conversions to get these quantities into the proper units before we plug into this equation. Ryan Spavels, would you be kind enough to help us do 0.05 arc seconds and to convert that into degrees?
Yep. So first you
I'm just going to write down what we're doing. Convert this to degrees. Okay, tell me what to do, Ryan Spavels.
first you times by a division bar.
Well, first you have to write down the
Uh,
number. Convert to
Yep,
degrees.
sorry.
Yep.
0.05 arc seconds times the division bar.
Yep.
Put arc seconds on bottom and arc minutes on top.
Okay.
Then multiply by another division bar. And put arc minutes on bottom and degrees on top.
Good.
Then you put,
Oh, by the way, Ryan, just to interrupt, for the benefit of other students, now my arc seconds will cancel. And now my arc minutes will cancel. All right, now we can put the numbers in last.
so for both bars, it'll be 60 on top and 1 on bottom.
Okay. Whoa. Are there 60 arc minutes?
Oh, no. Sorry,
I want everyone
Yep.
to watch out for that. That's one of the mistakes that's easy to make during dimensional analysis. You know the conversion factor, but you flop it upside down. You got to be careful to keep each number next to its units. 1 arc minute is 60 arc seconds. 1 degree is 60 arc minutes. Okay, punch them up and tell me what you get to 2 significant figures. Anyone, whoever's got it.
I ended up with 1.4 times 10 to the negative 5th degrees.
Can someone else confirm that?
I can confirm it.
Don't make that look like
what I got
negative
too.
50. Put that degree up and off to the side, so it's 1.4 times 10 to the minus 5 degrees. Okay. Ryan, Dick, can we convert the light years to kilometers?
Yep. Uh, 600 light years
Yep.
on to divide or multiply the division bar.
Yep.
Light years on bottom and kilometers on top.
Good. That will cancel out our light years. We need our conversion factor. Is that what you're looking up?
Yeah.
Should be in your lecture notes from last class, where I defined a light year under astronomical distances. Anyone else? Oh yeah.
One light years to 9.5 times 10 to the 12th or kilometers.
All right. So which one goes on top and bottom? Just to be clear.
9.5 times 10 to the 12th is on top.
9.5 times 10 to the 12 kilometers is 1 light year. Okay, punch them up. What do you get? By the way, it occurs to me, you guys know how to do this. So other students need to see, don't forget, new students, you're doing 600 times 9.5 EXP 12. That's how you do that. 5.7 times 10 to the 15. At the beginning of the semester, I often show people how to do every calculation because I know they'll struggle with that. And then as they get better trained, I just let them punch it. But I'm so used to adapting to my audience that since I know you guys can punch it, I forget that there are people out in the back who might be having trouble with that. So that's another reason why I might not want to be doing these homeworks with you guys. It makes it look too easy. You know what I mean? There's got to be a bit of a struggle there for people to learn. I want you guys to watch the videos, whether we do them live or not, because I want you guys to format correctly. By the way, also every now and then, there's some tricky astronomy stuff that I need to walk you through that's not obvious, okay? All right, we have our distance and we have our angle. Now we're gonna plug it into this formula. However, I'm out of board space, so I need to erase this. Ryan, Dick, do you have all that written down?
Yeah.
All right, can I erase this, guys? All right. Okay, so we're gonna plug into this formula here. The size of Betelgeuse is the angular size 1.4 times 10 to the minus 5 degrees. Notice that I keep my units when I plug in here, okay? Times 5.7 times 10 to the 15 kilometers times 2 times pi over 360 degrees. Okay. For the purposes of the people at home watching this, I'll punch this in so you can follow along. Wow, did I close? I keep closing the damn Logitech. Focus. Logitech, okay. So I want you guys to watch me punch this. All right. The right way to do things is to punch it all in one clean shot. So let's watch me do it. Clear out. 1.4 exp negative key 5, that's our angle in degrees, times 5.7 exp 15 kilometers times 2 times pi key divide by 360. And that's what you should get. Did you guys all get that? I expect the two Ryans to do it.
Yeah.
But, Sage, what should we round this to?
I would say 2 sig figs based on what we have.
Yeah, I like that.
Yeah.
So give it to me to 2 sig figs.
I have not put it through my calculator yet. Sorry, I was thinking
Oh.
about my graphic calculator in parentheses.
No, did you see the way I did it?
I did, yeah. That's what I was
elegant.
processing, and that's why I haven't typed it through yet. So I'm
All right,
sorry. I
well,
just need 1
come on,
second.
math major, punch into your calculator. That's what I'll say here. I want to take a little cat nap before lecture. Actually, we're running out of time for that, but.
I ended up with 3.4 times 10 to the negative 22nd.
What?
Haha. This is why I want my graphic calculator.
No, you're learning how to use this.
I
my
will.
friend, is a pistol. That is a
Yes.
bazooka, okay? So here, look, can you just follow along with me?
Yes.
1.4 exp negative 5 times 5.7 exp 15 times 2 times pi divide by 360, all in one clean shot.
Okay.
The cool thing about the EXP key is it glues the power of 10 to the number, so there's no PEMDAS issues.
Yeah, I wanted to put 2 pi over 360 in parentheses. Yeah. But so I ended up with 1 point, will that be 3 or 4? Probably 4.
4
Times 10 to the 9
units.
kilometers.
Okay.
Because we cancel
Box that up
out
because that's
degrees,
our
right?
primary
Yeah, we did.
answer. But there's 2 more little components to this. First, they asked us to calculate the diameter of the star Betelgeuse, and we have done that. What else did they ask us to do?
Compare the answer to the size of the sun and the Earth's sun distance.
Okay, let me tell you for everyone here, the Ryans already know this probably from working with me last semester. In our class, when someone asks you to compare, what you do is compare means take the ratio. I either want to know how many times bigger something is, or I want to know what percent it is of another thing. I happen to know Betelgeuse is pretty damn big. So we're going to take the ratio by dividing the big guy by the small guy. Let's compare to the sun. The size of Betelgeuse is clearly bigger than the size of the sun. The diameter of Betelgeuse is 1.4 billion kilometers over the sun's 1.4 million kilometers. A factor of how many times?
1,000.
That's right. Kilometers cancel. Betelgeuse is 1,000 times bigger than the sun. Now they ask us to compare to 1 AU, but they don't mean compare the distance to 1 AU. They mean compare the size of Betelgeuse to 1 AU. Betelgeuse is bigger than an astronomical unit. If we divide the size of Betelgeuse by 1 AU, we have 1.4 billion kilometers. Remember that 1 AU is 150 million kilometers. Use your calculators and punch that up. Sage, anyone? Sage, you're not doing stuff like type in times 10, are you? That would give me the willies. You use your EXP key. All right.
I got a 9.3 and that just seems small.
Why does that seem small?
I don't know, because I was thinking like if we replaced Betelgeuse with our sun, we'd get engulfed in flames.
Wait, I'm sorry, say that again?
Because an AU is our distance from the sun, yeah?
Right, yeah.
So if Betelgeuse is bigger than an AU, if we replace the sun with Betelgeuse, we'd just be engulfed in flames. I was thinking about that, and 9.3 seems small.
Small in comparison to what?
I'm not sure. I haven't worked with these numbers before. I just wasn't sure.
I think the point of this is exactly, now I wouldn't use the term flames. I would use the term plasma, but okay.
Yeah.
But the point of this is that not only would we be engulfed, what does this 9 mean, Sage? This 9 means what?
It's 9 times bigger than an AU.
Or in other words, 9 AU. Right?
Oh, yeah. Yeah.
9, but okay, let's say it the way you did. 9 times bigger than 1 AU.
Which actually, that puts it back into perspective. That's still pretty big.
Exactly. Like when you were saying small, I was like, what? What are you talking about? Small? I don't think like. In fact, look at it this way. Let's use the slide.
I think like logically, I knew it would be a gigantic physical thing, but 9 seemed like a small number. So I was like,
Look, if you put Betelgeuse in our solar system,
Oh my God, I'd take out Jupiter.
yeah, right? So here's-
Okay.
if you, so 9AU, like, that's Betelgeuse if you plopped it into our solar system.
That'd be
It
crazy.
would, Betelgeuse would, and let's find that previous slide there, where I have the solar system. Betelgeuse would take out Mercury, Venus, Earth, Mars, Jupiter, and almost make it out to Saturn. So it would swallow quite a few planets, wouldn't it?
Yeah, 100%.
Oh, and by the way, remember, that star can easily be seen on your sky during the wintertime. It's right here. That's,
And Orion, that's right.
yeah, it's the upper shoulder of Orion. That's Betelgeuse.
That's so cool.
Right? Isn't that cool? That's kind of a neat problem.
Yeah.
Betelgeuse is one of the biggest stars. We've actually found stars bigger than Betelgeuse, but not very many of them.
Hmm.
Betelgeuse is about as big as a star can get in terms of its radius. You'll learn about that later. Okay, look, we used up our time and we finished our homework. That's great. Now listen, for the three of you, don't delay. Take photos, submit them to homework 1. A few people were asking me about how to do that. Let me just show you once again. To submit your homework once you've completed it, and you should do it right away, take a photo. I recommend that you send it to your computer first. When it's uploaded from your computer, that seems to work a bit better. To answer the question, people are like, how do I upload a video? Well, first of all, watch my damn videos because I'm showing you how. Okay, so now you're watching my damn video, and now browse local files and upload it. Let's take a quick peek at the grading center so you guys can see what it looks like on my end. Notice that in our class, although we have 28 people registered, only 9 people so far have turned in their lab 1. That's okay because you have until Sunday, but let's just see how people are submitting things and what it looks like. I think I did this last time with you, right? That's good. I think we did this last time actually, so I might be wasting my time. That's all right. That's fine. At least I can see. I just want to make sure that your previews are coming up. You know what I mean? Okay, this, oh, weird. This is not a, oh, okay, Ryan, you submitted one of the pages we didn't do. I see what's going on. This is okay. It would be nice, you don't need to, if we don't work on a page, Ryan, don't bother uploading that. That just confuses me when I'm moving fast.
I
okay?
just have been using a printer to scan it in, and I just do double-sided.
Okay. Oh, I see. That's fine. Tiny scanner seems to be the way to go, says Sage. Okay, cool. See, there are nice notes that people send me here, giving me tips on what's working for them. Tiny scanner seems to be the way to go. So take it from Sage. Anyways, it looks like everyone's kind of doing, Brandon, I think you're still here in the Trolliverse. That looks good, Brandon. So, okay, so you guys already know what to do. I'm wasting my time explaining this. Upload your homework. What do you say we take a little break before we do the lecture component? You want to do like a little 10-minute pause? We've been grinding for an hour or two here. So even though it's 12:07, who cares? Let's, I'm going to stopwatch. I'm setting a timer for 10 minutes. And I'm coming back when this runs out. Sound like a plan? All right, boom. Tea break is on. Tea break 1. I'll see you guys in a little bit. Welcome back, Astronomy 1020. Time for the lecture portion of this class. This is lecture 2. We're going to do angles, and we're going to do the local sky, and we're going to build up towards coordinates. In our labs today, we're going to use that guy up there. We're going to use one of those celestial spheres and find the locations of some of the most famous stars. I got a little behind today, so I'm going to pace this rather quickly. I don't think that's a bad thing. I think it'll cut down on the length of the video. I need to do a few modules with you guys in terms of notes. Last class, we did a little module on the orbit of Earth where I defined things like perihelion and aphelion. I defined the ecliptic and things like that, right? Did I do the 4 key points in Earth's orbit, the spring equinox, the fall equinox, those things?
I don't think so, no.
All right. That's a little add-on that I need to squeeze in before I go further. I'm going to need to come back to these concepts later today, and I'd like to squeeze that in. So if you guys are looking at your notebooks and you want to cohesively organize this, there was a section in our notes last class called Earth's orbit. And I would like to add to that section. To start off with a slide. Oh, by the way, Ian, since you weren't there for the homework session, you'll go back and watch that video later, right? Yep. A note to you guys, it takes a while. These videos are way longer than the spring semester ones. It's 2 hours homework, 3 hours lecture, 1 hour lab. It took like 2 to 3 hours to process this video. It was over 5 gigabytes. So that slows down the turnaround time. Anyways, during the orbit of Earth, let's look at a very important picture here. You guys learned that the Earth orbits the sun on a path that we call the ecliptic path. The ecliptic path is the circular orbit of Earth, or the quasi-circular orbit of Earth. Notice that Earth's tilted, its axis spin is tilted by the famous 23.5 degrees with respect to the ecliptic plane. Okay, if you really look at the details, it's tilted, the North Pole is tilted 23.5 degrees with respect to the perpendicular of the ecliptic. Whatever, too long, didn't read. It's just easier to say tilted with respect. On the other hand, the equator by geometry is also tilted by 23.5 degrees with respect to the ecliptic plane. So either way you cut it, it kind of boils down to the same thing. Rather than say tilted with respect to the perpendicular of the ecliptic, one just says the Earth is tilted 23.5 degrees with respect to the ecliptic plane. What I want you to focus on for a moment is that that tilt maintains the same orientation in space. In the diagram here, you can see that it's tilted up and to the right towards Polaris. And as it kind of orbits around the Earth, could I move a little arrow? If I draw an arrow, can I move the arrow? Ooh, that's not the direction I want. I want it to go like this. Could I move that arrow? Yeah. Oh, this is cute. As Earth orbits the sun, it kind of keeps that axis tilt pointed in the same direction. Do you see what I'm trying to do there? You see what I'm trying to do? Okay. Because of this, the axis tilt of Earth makes 4 key geometrical alignments with the sun that have a kind of big impact. For instance, let's consider the point when Earth's, actually, wait, let's see how jazzy I can make this. Could I do this? Okay, now can I move both of them together? Oh, nuts. Okay, well, you can't win them all. Let's just grab the arrow. When Earth is in this configuration, the 23 point, can I tilt that a little bit? That would be nice. I got an idea. Let's clear drawings. Let's use blue for Earth. Just humor me here for a sec, guys. I'm trying to do a thing. And let's make this really, yeah. I'm trying to get the angle just right. See that? Okay. As I play around with this thing, I'm trying to find cool ways of using visual aids. All right. So here comes Earth. It's keeping its 23.5 degree axis tilt. Let's talk about when it gets to this point right here. If you put on your 3D thinking caps, at this point, the axis is still tilted 23.5 degrees with respect to the ecliptic plane, but it actually makes a 90-degree angle with respect to the sun. And for this, it might be helpful to do it here. Let's pretend that you, the observer, are the sun, all right? On the day of the spring equinox, the Earth moves into a configuration where the equator is perfectly lined up with the direction of the sunlight. And because of three-dimensional geometry, the axis is still tilted 23.5 degrees with respect to the ecliptic plane, but it's also now at a 90-degree angle with respect to the sun. Notice that is not true a day before the spring equinox. When the Earth is a little back here, it's not quite a 90-degree angle with respect to the sun. Right here on this particular day, which is usually around March 21st, that's the spring equinox. Likewise, as Earth goes around the sun, it'll eventually come into a configuration where the North Pole is sort of aligned. The tilt of the North Pole points towards the sun. On that one day, that is the summer solstice. And so these points, these key points in Earth's orbit, originally, conceptually, are geometrical alignments between the tilt of Earth and the sun. Let's look at a cute little diagram to help with that here. These are the 4 key points in Earth's orbit. And we're going to take notes on this in just a second. So we have here the spring equinox. Notice, by the way, that even though the Earth is tilted, on the spring equinox, the northern hemisphere and the southern hemisphere get equal amounts of sunlight. So there's sunlight here and there's sunlight on the bottom, okay? When Earth slides towards the summer solstice, the sunlight beats down more directly on the northern hemisphere. And although it hits the southern hemisphere, it does so at an oblique, shallow angle, all right? This is the summer solstice. This is the fall equinox. This is the winter solstice. And because each point in Earth's orbit is related to a day in the year, there are dates for these things. So I call them 4 key points in Earth's orbit. The spring equinox occurs around March 21st. The summer solstice around June 21st. The fall equinox, September 21st. And the winter solstice around December 21st. Do you know that a lot of this early astronomy stuff was worked out by like Babylonian astronomers, like pre-Egyptian societies in the, what is it, the Mesopotamia or something? Because they were agricultural societies, they needed to keep track of the motions of the sun and stars as a sort of calendar. That was their iPhone calendar back in the day. We know that the Egyptians knew that there was not an exactly equal number of days in a year. They knew that a year was not just 365 days, but something close to 365 days in a quarter. Now, it depends upon whether you're talking about a tropical year, which is our calendar year, or whether you're talking about a sidereal year, which is the true orbit. Do I want to get into that? I don't know. Since we're talking about calendar dates, let's talk about a tropical year. A tropical year is 365.24, and there's extra digits there that I can't remember. 365.24 days. A sidereal year is 365.25 days. It's a difference of about 20 minutes. Look it up, okay? For this reason, because there's not an equal number of days in a year, to keep our calendar synced up to the seasons and the points in Earth's orbit, we have to introduce leap years and other tomfoolery to keep our calendar synchronized to the seasons. That means because we do a leap year every 4 years to correct for this, the date of the spring equinox and the fall equinoxes can drift from anywhere from the 20th to the 21st to the 22nd to the 23rd. And I hate to say it, but every now and then it'll even pop up on the 19th. It can wiggle around by a few days. So we're going towards the summer solstice now, just for fun, demonstration purposes and entertainment. Summer solstice 2021. It's going to occur this year on June 20th. I ask the students just to memorize it as the 21st. That's just a good rule of thumb. Do you guys see that there's also an exact time of the equinox or the time of the summer solstice? What's that about? Let's think our way through that problem here. Why would there be an exact time to the summer solstice?
probably because the Earth doesn't stop moving, so that's the exact moment it gets to the angle.
Dude, I couldn't have said it better myself. During the course of the summer solstice, when Sunday, June 20th comes, Earth will be still moving along its orbit during that day. In fact, the spring equinox or the summer solstice, they're actually like a moment in time. And that moment in time is the exact moment when the North Pole slides into direct alignment, poking most towards the sun, right? A moment after it's not exactly aligned, a moment before it's not aligned, but it's spinning in this moment right there, when the North Pole is pointed towards the sun, that's the summer solstice. Likewise, the exact moment of the spring equinox is when the equator perfectly makes a 90-degree angle and the equator points towards the sun. Now, because of this, I need you to think about that, and I need you to get even crazier with me here. Let's take the following set of notes. It relates to today's lecture. May I erase? Okay, here's something to confuse the bejesus out of you. The spring equinox is 4 things at once. Okay, it's at least 4 things at once. It is one, first and foremost, a geometrical alignment, or a better way to say that would be a point in Earth's orbit. That's the first way we thought about it. Secondly, the spring equinox is also referred to as a calendar day. Somewhere around March 21st. As we just discussed, the spring equinox is also a moment in time. 4. Okay, for the 4th thing, now imagine that you are a human stuck to planet Earth. That makes you what we call the observer, and you're observing the cosmos from the ground. Let's see how that changes the perspective. We don't actually observe the Earth going around the sun from this perspective. This is the flying saucer perspective that visiting aliens get to see. But unless you're one of the few lucky people to have gone into orbit, you don't actually get to look at the Earth this way. You look at it from the ground. If you do look at it from the ground, things become a little bit different now. North Pole is up, South Pole is down. There's the equator. We'll define the celestial equator today. That's the projection of Earth's equator. Now the ecliptic is not the path of the sun, but this now becomes definition number 2 of the ecliptic. Do you guys either remember what that is, or are you willing to regurgitate it for me from your notes? What is the second definition of the ecliptic? How do we think about the ecliptic from an Earth-based perspective?
The path of Earth around the sun. You said not the path of the sun, right?
Wait, hold on. The original definition is the path of Earth around the sun.
Okay, yeah.
What is definition?
Path of the sun against the background stars.
The path of the sun against the background stars. In other words, I have a couple of different pictures that might show this here. If we watch day after day, the sun seems to drift by about 1 degree along the ecliptic each day, right? So from our perspective, the ecliptic is also sort of the path of the sun against the background stars. But what that means is now the spring equinox can be thought of in a whole different way. The spring equinox is not only a point in Earth's orbit, a day, a moment in time, but the spring equinox is also a point on the sky. It's the point on the sky where the ecliptic and the celestial equator meet. And there is a literal point on the sky that corresponds to the spring equinox. I have it somewhere over here. The exact point on the sky that we associate with the spring equinox is this point here, just below, but still inside of the constellation Pisces. There's nothing there for you to see, and yet this point will rise in the east and set in the west, just like any star, sun, or moon every single day. The spring equinox is probably rotating through our sky right now. Every now and then something does appear at the spring equinox. I love to play this game with students, but I bet one of the Ryans or Ian will remember. Once a year, a special star will appear at the spring equinox for one day only. What is that? Once a year, a special star appears for one day only at the spring equinox. What is that star? Really? You can't think of the special star that appears for one day only at the spring equinox? It's the fucking sun, okay? That's where the sun's gonna be on March 21st.
See,
And
that
let
was
me-
a trick question. I thought you'd already said the sun was going through there. So I didn't
The
want to
sun is
say
a star. It's not a trick question. That's where the sun's gonna be in the summer solstice on June 21st. That's where the sun will be on September 21st. I mean, it was kind of a trick question, but I wanted to see if you could figure it out. I wanted to see if you could figure out that the significance of that point is that that's where the sun will be. The spring equinox also means that's the point on the sky where the sun will be located on March 21st. Do you see what I mean? So therefore, the spring equinox is four things at once. A point in Earth's orbit, a day of the year, a moment in time, and also a point on the sky. And this is going to be an issue for today's class because we're going to use that point as the basis of one of our celestial coordinates. I've got some harsh glare. Let me see if I can do that, deal with that. Yeah, that's better. All right. Before we can do coordinates and stuff, we got to talk about angles. May I erase? New module. Oh, by the way, because of that conundrum with the spring equinox being all kinds of things, I love to remind students that I could ask you a test question that goes like this. Describe the location of the spring equinox at noon on the spring equinox. Oops. Think about that one. There is an answer to that question. Okay. Let's discuss angular size and angles in general. I did a little bit on this in homework. Now we introduce it properly. Angular size. The symbol for angular size, in honor of the Greeks who loved geometry, for now is the symbol theta. You don't even have to know that it's called theta. I'm just telling that to you. It's the little circle with the line through it. I think they probably do this in mathematics too, but in physics and astronomy, it's considered classy and cool to always use Greek variables for angles so that the reader will kind of look at an equation and the first time be like, oh, that's probably an angle because they used a Greek letter. Not always true, but sometimes we do that in astronomy. So the key idea behind angular size is that you see angles, not sizes. I demonstrated that during our homework session today. Another kind of classic demonstration of this is if you go out at certain times of the night, see if it's slide 30 here. Sometimes you go out at around dusk, maybe around Halloween or something, and you'll see the full moon coming up over the horizon. and you see this big evil orange moon coming up over the background of buildings, and you say, whoa, check out the moon. The moon is huge, right? Have you ever seen that before, where the moon just looks big and awesome and scary? Usually it looks orange too, because you're seeing it through a longer column of atmosphere. This is actually known as the moon illusion. What you should do the next time you see that huge moon is hold your finger out at arm's length and compare the full moon to the width of your fingernail. And you'll discover the full moon is about half the width of your finger. Later on at night, as the moon gets higher in the sky, it will lose its oranginess, but it will also no longer look huge to you. It'll just look like the moon. Take out your finger once again and hold it up against the moon, and you'll discover it's still only half the width of your finger. You have been a victim of a perceptual or psychological effect called the moon illusion. See, your brain is hardwired to know that if you're looking at the moon and you're seeing it against a foreground of cactuses and buildings and mountains and trees, if it's half the width of your finger and it's still behind all that stuff, your brain thinks, holy cow, that thing must be really big. Once the moon goes up onto the sky, you lose all sense of depth perception, and your brain doesn't really have a good way of judging how big or small it is. Think about the moon. The moon doesn't look particularly big or particularly small. It's just kind of there, and you can see it, but it's hard to get a feeling about what's going on there. Your brain is hardwired to do math whether you realize it or not. It's hardwired to know that you see things as angles. You need to know when you see the little tiny bear on the horizon that by the time it gets up to you, it's going to be a big scary bear, and the time to run is now, right? So your brain has to know something intuitively about angles. You can even see it here in the camera. When an object is close, it subtends a big angular size. When it's far away, it gets smaller. So, and angles are true about things in your field of vision that are not on the sky. This marker, for instance, subtends some angle in not only my field of view, but even in your camera's field of view. This has some angular size. One thing I have to do often when I attach cameras to the telescope is say, how many degrees does this camera span on the sky? What is its plate scale, so to speak, okay? Okay, so the idea is that you have an astronomical object. It has a diameter S. You're looking at it subtending some angle. This is a good picture to draw. It's located a distance d away, and it has an angular size theta. The angular size is related both to the size of the star or moon and the distance to the star or moon. So here, S represents size or diameter. And for now, for intro beginning students, it could be in kilometers. We can play a little loose with the units here. D is the distance to the star. For now, we'll assume it's in kilometers, but later on we'll relax that restriction. And then theta represents the angular size in degrees. These things are related by the legendary small angle formula. From our homeworks today, S is theta times D times 2 pi over 360 degrees. That's the version that comes from geometry, where you're solving for the size of the star. My marker is starting to die here. Do I have the right one? I should mention that sometimes in our homeworks, and especially on the exam, instead of calculating the size of the star, I might, like we did in our homework today, there might be times where I'd rather have you calculate the angular size of the star. We can do some algebra, which I'll leave to the reader's imagination. And I can rearrange this formula to solve instead for the angular size. If you wish to compute the angular size of a star, a nice rearrangement of the formula is to say the angular size is 360 degrees over 2 pi times the size divided by the diameter. We're actually going to use that version in our next week's homework, next Tuesday. They're both the same formula, they're just solved for different variables. I could show you the algebra, but anyone who's good enough to know what I'm doing could do it on their own, and anyone who isn't going to give a shit. So I'm just going to just show you the answer, okay? All right. Now that we've gotten that out of the way, I know that probably makes sense to the guests that I have here today. We should talk about, for the sake of our other students, the fact that there are different units we could use for angle, and let's think about why. The default angle that we've chosen to use for the small angle formula are degrees. And degrees were invented by Greeks who decided that, you know, and actually this probably goes back to Mesopotamian astronomy. All of this 60, what do they call it, sexagesimal? Why 60 minutes in an hour? Why 60 seconds? The Babylonians didn't like decimal systems. They liked dividing things by 6s and 3s. And I bet that had something to do with astronomy. I bet it had to do with dividing the sky up into 3 parts in the morning and 3 parts in the evening. And that's probably how they became obsessed with 60s. Remember, Sage, astronomy is older than mathematics. Think about that. Astronomy is older than science. Astronomy is older than physics, and astronomy is even older than mathematics. In fact, mathematics was probably invented because of the need for astronomy, because of the need for calendar keeping, because people like to eat and not have to stab each other to get a snack, you know? So growing crops and all that is important. The Greeks decided to kind of continue this system, and they divided a circle up into 360-degree wedges. Each one is a degree. That's great if you're drawing a little circle on a piece of papyrus. But when the circle is your sky, a degree turns out to be a pretty crappy, clumsy unit, right? I mean, the moon and the sun both have an angular size of half a degree, less than a degree. And they're the biggest astronomical objects we should look at. I should mention that astronomers often use their outstretched hand as a cheap angular measurement tool. Your finger outstretched at arm's length subtends about 1 degree. Your fist at arm's length is about 10 degrees. And if you do the Hawaii hang 10 thing, 25 degrees. And astronomers will often use their hands outstretched as a kind of rough and ready angular measurement tool on the sky. Let's take some notes on this. There are 3 units for angle. That we will encounter in this class. There are many others, but these are the ones that we will use. Actually, guys, I'm starting to think that the dirty dry erase board is killing my markers, and it was cool when CCRI was paying for it, but now I am suddenly, it's taking on some more urgency. So hold on a second here. You guys can't see it in the video, but this board gets real crusty and nasty. And it eventually starts to affect your ability to read what I write. All right. 3 units for angle. We have the degree. 1 degree could be defined as a 360th of a circle. However, a better conversion factor expression is one circle contains 360 degrees. That's the one that we all know and love. This is, most of you know this, even people who don't do a lot of math. As an example, Gratius, the angular size of the moon turns out to be damn close to half a degree. By a curious coincidence, the angular size of the sun also half a degree. Now, you got to think about this, guys. Because of this, because the angular size of the sun and the angular size of the moon are equal to a half a degree, that means human beings get to experience the magic of things like total solar eclipses, when the disk of the moon perfectly blocks the disk of the sun and creates darkness during the daytime. Is the moon the same size as the sun? The sun's way bigger. Is the moon the same distance as the sun? The moon is way closer. Could you imagine if we had grown up on a planet where the conditions were ever so slightly different in the beginning of our solar system? What if the moon had just formed a little bit bigger or smaller? What if Earth had been a little closer or farther from the sun? What if I mean, what an extraordinary coincidence that our moon and our sun, totally different sized bodies, totally different distances. The moon is 400 times larger, I think, in diameter than the moon, or 4,000 times. And it's also something like 4,000 times farther away, something like that. They're perfectly balanced. Now, probably seeing stuff like this contributed to people's interest in understanding astronomy. I wonder on another planet, if you didn't have this coincidence, I mean, it literally might take the sun to be blotted out during the day for people to say, what's going on there, right?
It makes a lot of sense how you could see that as something religious or
Totally
relating to a god. Because, like, what are the chances?
Right. There are almost no coincidences that I know of in astronomy, except for that one. And I think about it all the time. Like, it's just preposterous, right? Anyways, remember that the sun and moon, being the largest astronomical objects that we see, are still less than 1 degree. So astronomers are interested in studying stars and galaxies. We need really tiny angles for astronomy. And for that reason, we've subdivided the degree into even smaller units of angle. You probably already got a sense of them from homework, even if you are a new student. Here's a quick slide on them. Take a degree, slice it into 60 more little pizza wedges, and you have an arc minute. An arc minute is kind of like the equivalent of looking at a soccer ball from a half a mile away. Ironically, the angular size of the planet Jupiter is roughly 1 arc minute. Arc minutes are good for describing the angular sizes of planets. The angular sizes of stars require an even smaller unit called the arc second. That means you take an arc minute, subdivide that into 60 pieces. So let's write that down in our notes. An arc minute has the symbol 1 minute of arc, the apostrophe. It's 1/60th of 1 degree. The conversion factor, 1 degree contains 60 arc minutes. Arc seconds, a 1 with a double apostrophe, defined as 1/60th of 1 arc minute. Our conversion factor is 1 arc minute contains 60 arc seconds. I know that you guys know all about this, Ian, Ryan, because we did this a lot, and these are basics of astronomy that all my students need to learn. So you guys know this stuff, but I want to get those notes down for new people like Sage and other people who aren't as familiar with it. Good things to know about: the angular size of the planet Jupiter, roughly 1 minute of arc. The limit of the human eye at 20/20 vision, if you have a good eyeball, the limit of human vision a good eye has an angular resolution, a minimum angular resolution of roughly 3 arc minutes. So you can see things that have an angular size of 3 arc minutes or greater, right? I don't care how far away it is. It could be a quasar at the edge of the observable universe. It could be a paramecium floating around in your eyeball. Bigger than 3 arc minutes, you can resolve it. Smaller, you can't. And in fact, here's a piece of info that you cannot get from the book, but that is so important, I think, to understanding astronomy. Can I erase this here? All right. A little lesson on optics and observing astronomical objects, real quick. There is a difference between resolved objects versus unresolved objects. They don't teach this to you until you take an optics course, but I think it's imperative to understand this, and it's not complicated. When an astronomical object is resolved, you see that object as a disk, okay? And that means that you can distinguish between the top and the bottom at bare minimum. And in the case of like the moon and the sun, you can even see surface features. Like you can see those little Maria, the man in the moon or something, right? When an object becomes smaller in angular size than 3 arc minutes, it becomes an unresolved object. You can still gather light from an unresolved object like a star, but you cannot see it as a disk or make out any features. It's what astronomers refer to as a point source. A point source is unresolved. It's a little speck of goo. You can detect light from it, but you can't make out any features on it. As a dramatic demonstration, my friend Bob Horton took this beautiful photograph. Oh, shoot, I just forgot the damn number. I'm stupid today. Was it 77? Oh, sorry, 44. Function F5, 44. Here's a picture of downtown Providence seen from the roof of the Barris and Holly building near Thayer Street at Brown University. And it's a beautiful photograph of the nighttime of Providence. And he's got 3 famous objects here in the field of view. This is the brightest star in the sky. It's the star Sirius, which will come up in our lab today. You'll notice that in this image, Sirius doesn't look very bright. That's because he's exposed the photograph for the much brighter buildings downtown. This was taken for aesthetic purposes. When you stand outside, even in the city, you can tell Sirius is a bright star. Now, next to it, we see 2 planets. The top planet is Jupiter, and the bottom planet is Venus. Venus is actually brighter than Jupiter in our sky. Notice that the light from the planets is much brighter than the light from stars. That's one basic way you can tell a planet apart from a star, is they're just way brighter. Another famous rule of thumb that astronomers use is stars twinkle and planets don't. That is also related to their angular size. The idea is because planets have an angular size of about 1 arc minute, the beam of light that comes to Earth is a bit more steady and can kind of punch through our atmosphere. The angular sizes of stars are such a small fraction of an arc second that that beam is so narrow that it can get flickered around by the motion of molecules in our atmosphere. Hence, the pencil-thin beams of stars twinkle, but planets don't. Yet, because planets are smaller in angular size than an arc minute, your eye cannot resolve neither planets nor stars. Planets basically just look like stars. They look like point sources, just much brighter and much steadier. Do you see what I mean? In the following image, he takes a small telescope or a telephoto lens, he attaches it to the camera, and he zooms in on the 2 planets here. And now notice what happens. Suddenly, we can see Jupiter as a disk, And you can now see the 1, 2, 3, 4 Galilean moons next to it. Those are the famous large moons of Jupiter. Here you can see Venus, and notice something cool about Venus. Venus is special among the planets. I mean, Mercury might do this too, but Venus is one of the only planets that goes through a set of phases, just like the moon. And I believe we're seeing it here in a gibbous phase. Let's have a test. Is Venus resolved or unresolved in this image?
I would say resolved. You can distinguish a top and a bottom.
And you can see the phases, which you would not be able to see if it was a point source. Is the disk of Jupiter resolved or unresolved in this image?
I would say resolved as well.
Because that's probably truly the top and truly the bottom. Through a small telescope, you can even see stripy features. How about the Galilean moons?
Unresolved. They're just points.
They're just points. So I think my point that I'm making is that arc minutes would probably be good for expressing the angular size of Jupiter and Venus in this image. But if we were going to think about the angular sizes of those moons, we'd probably want to use arc seconds. And stars are usually so small in angular size that astronomers prefer to measure them in milli-arc seconds, in thousandths of an arc second. So oftentimes when you look at a star in Wikipedia, rather than saying Jupiter as they did in our homework today, they won't say Jupiter is 0.05 arc seconds. What they'll say instead, you can see it here in this slide, 40. They'll say the angular size of Jupiter is 55 milli-arc seconds, which means 0.055 arc seconds, right? Okay. Now we know everything about angles. Now, stellar coordinates. By the way, we'll build in a lot of tea breaks today. We normally take it at 1:30, but let's take it around 1:45 since I kind of started late. Does that sound okay? I think we can get maybe 1 or 2 little modules in here. I'm going to try to set an alarm. Oh, damn, they changed the iPhone. 1:45 p.m. All right. That's just to, I get yapping and I can lose half an hour without even blinking. So, okay. We need to develop a model of the sky in which we can track the rotations of stars. Ian and the 2 Ryans will remember that this was one of the more complicated parts of 1010. So you're going to benefit from a going over. Sage, some of this stuff will be new to you, okay? The Greeks, the Egyptians, the Mesopotamians, the Greeks in particular were more philosophical. They literally believed the stars were stuck to a crystalline sphere which rotated around Earth. We now know that, of course, that's not true. There's a whole big universe out there and stars lie at different distances, but who cares? For the point of view of an observer on the ground, this might as well be true because you're watching a rotating sky over your head that for all intents and purposes is a rotating sphere, right? So this concept, the concept of the celestial sphere is useful, especially when you're trying to orient yourself on the sky and think about how stars move in your local sky. You might think it's simple, but it is not. As a starting point, let's put a name on this structure. I'll try to go through this stuff quickly, but I don't want to do it too quickly. Let's call this thing the celestial sphere, and let's identify 3 points on it: the north celestial pole, the south celestial pole, and the celestial equator. The celestial sphere is a useful lie. The celestial sphere could be defined as a sphere of infinite radius on which stars, planets, moons, etc. seem to rotate. Note the infinite radius, that's a key part. we can also identify 3 points on it. The north celestial pole. Going forward, you'll hear me refer to this by an abbreviation or NCP, or an acronym, is that right? The North Celestial Pole is the projection of the Earth's North Pole onto the sky. The celestial equator, we will abbreviate as CE. And because I think you guys probably get it, it's the projection of the equator onto the sky. And then the south celestial pole, SCP, is the projection of the south pole onto the sky. There is a famous object, a famous star located at the North Celestial Pole. You guys know what it is, right?
Polaris.
Yeah. Polaris, wow, my handwriting's weird there. The North Star Polaris is above the North Pole, but that does not mean it's above you in your local sky. As a demonstration, if you take a camera and you point it towards Polaris, set it up on a tripod, and you leave the shutter open for several hours during the night, as Earth spins, you will watch as all the stars in the sky seem to rotate, spin, and orbit around Polaris. In fact, you can see that even Polaris is actually rotating here. What does that suggest to us?
It's not perfectly over the North Pole.
It's actually off by half a degree. But we frequently just pretend like it's at the North Celestial Pole. I actually had to do a polar alignment to the CCRI 16-inch telescope with this big heavy mount. And there's nothing, you need it to point exactly at the North Celestial Pole, but there's nothing there to guide you. And oh my God, was it such a headache. You have to track 2 different stars, one south along the celestial equator, one east or west along the celestial equator, and you have to stare at it with a crosshair. And if the star starts to drift in one direction, you take these big wrenches and you torque the telescope. Oh man, me and friends sat there all night doing that. And we didn't do a perfect
job. It's such a small measurement too, that's so hard to get that precise.
And there's a couple of different ways to do it, but it's real tough. Anyways, people make a cottage industry out of taking these photographs of stars. Circumpolar stars are stars that never rise or set because they're too close to Polaris. This star is circumpolar. That star is not because it sets. So all stars seem to spin around Polaris, but some are called circumpolar stars. That issue is going to be in your homework next week, and it's going to cause you some pain.
What are those stripes on the bottom left?
Probably cars going by on the highway, because he was
like
probably
a little above it in the sky.
He was probably at some car park, and he probably did this for maybe 3 or 4 hours. And during that time, a few cars probably drove by, or they could be actually no. See how
there are tiny white ones in the circles.
They're probably other astronomers who are walking by with a red flashlight or something. Definitely somebody walked by.
I think I see what Sage is talking about. Like not below the horizon, like above it on the left. They're like
in the sky.
Going like
those things.
Those a little above it even.
Those are meteors. Those are meteors. Those are
okay, cool.
Shooting stars.
That's what
During
you
the
feel. That's what I
Yeah,
figured.
during the course of the exposure, probably a few meteors went by. That's what I'm
it.
guessing that is. Yeah.
My guess was a plane.
Yeah.
Maybe. Yeah, actually, I never even noticed that before, guys. So nice observation powers. It's possible that you're correct there too, Ian. Okay. What we're going to want to do next is we're going to want to make a model of our local. Oh, wait, we need to take one more data point about the celestial sphere. This is extremely important. You can always see exactly 1/2 of the celestial sphere in your local sky, not an obvious point. All right. So if you guys go back here, let's look at this picture. We tend to think of ourselves as being a little person on a big Earth. And when we imagine standing at a place on Earth, because we're a little person compared to big Earth, we tend to think that our sky is like a little dude sky surrounding our heads. In fact, the sky over your head is a big dude sky. Your sky encompasses always exactly 1/2 of the celestial sphere. So your local sky is all of the green stuff. The problem is that when they say a picture is worth 1,000 words, a good fraction of those words are lies. And this picture tells a lie because it shows the Earth as large in comparison to the celestial sphere, right? A better demonstration of the celestial sphere, more appropriate to scale, would be to represent Earth here as a microscopic little dot, and then to represent the celestial sphere as a big massive circle surrounding it, such that if your head is pointed in this direction on Earth, if you're at that position on Earth, there is no difference between the line that cuts through your feet and the line that cuts through the center of Earth, because Earth is microscopic. So in fact, if you're standing with your head pointing in the direction of the arrow, all of this is actually what's in your local sky. So ignoring things like buildings and trees, your local dome of the sky always encompasses exactly 1/2 of the celestial sphere. That's important enough, I think, to take it as a note. You always see 1/2 of the celestial sphere. Sorry about this. In your local sky. Okay. Speaking of the local sky, we need to learn how to draw that and identify some vocabulary terms on it. I'm erasing. All right. Next up, we make a model, a drawing of a 3D view of our local sky. Get out those rulers. If you guys bought a ruler, you're gonna want them. It's time to do a little Bob Ross, okay? So we're gonna make a 3D view of the Rhode Island local sky. We're gonna make this picture careful the first time, and then you'll have good ideas about how to make it next time. Take out your ruler. I'd say on your page, probably about 10 centimeters or 12 centimeters would be a good length for the base. Leave a lot of headroom and make a line about 10 centimeters on your page, okay? Mark the midpoint at 5 centimeters. We want to draw a dome of the sky. Let me give you some tips on how to do that. I like to take the radius, which for you guys is about 5 centimeters, and I like to measure a few different dots at different distances from the center. That will help you make a sort of better diagram. You know, stop me if I've said this before. A nice, neat diagram makes things easy to see the relationships of. A poor diagram is almost unhelpful and confusing. Now I'm going to kind of connect the dots to make the best dome that money can buy. This is a 2-dimensional dome. We'll make that sometimes. Let's bring this into 3D by putting a dash just above and below the midpoint. And then I'm going to draw in an oval and kind of connect the edge. All right. Got all sloppy there at the end. I imagine that a good artist, when they're drawing, could probably see what the line is going to be. I can't do that. All right. I've never had art skills.
If you really want to get into it, you have to do vanishing point, but that's a whole thing. So
Yeah. Let's shade in. I'll use green to shade in some grass as if we're standing in a field. Yeah, I once or twice in my life I've had to make some of those perspective drawings, and they're difficult and fun at the same time.
yeah, they suck. I hate them.
It's imperative when you draw your 3-dimensional local sky that this is the thing students always forget to do. You've got to decide where north is. Because I am a right-handed person, and because I have diagrams with north on the right, I always like to put north on the right-hand side. That's my instinct. So this will be north. This will be south. This will be east. And that will be west. The observer is here in the middle of the field. Okay. We've now drawn a 3D view of your local sky. The local sky is a hemisphere. It's half of the celestial sphere. Let's draw a line from the observer straight up overhead. Mark it with a Z because that point is called your zenith. The zenith is the point overhead. The next vocabulary term we have is the horizon. A 360-degree ring at the base of the local sky. In other words, that's the oval there that we just made. Hey, Ian, a moment ago you were mentioning vanishing points and perspectives, right?
Yeah.
Here's something to think about, bud. In astronomy, the horizon is the same thing as you make when you do those perspective drawings and do a vanishing point, with one important distinction. When I was a kid and I drew these perspective drawings with a vanishing point, I imagined the horizon to be a point on the ground. From now on, the ground is boring, and we're interested in the sky.
Yeah. The
horizon is also a point on your local sky, and stars can rise or set when they appear at the horizon, right? So try to twist your mind to astronomy perspective. The horizon is a point on the local sky. Barely, but it's there. All right. Next up, we can describe this arc here. It's the arc that runs north to south and cuts through your zenith. It's going to divide your local sky in half along a north-south line. That's called the meridian. The meridian is an arc that rises due north reaches the zenith and sets due south. The importance of the meridian can be seen here. And let me give you all a sneak peek of where we're going. Our goal today is to describe the motions precisely, accurately, whatever. Describe the motions of stars, oops, as they move through our local sky. Function F582. These rings, which are sometimes called star tracks, sometimes are called diurnal cycles. This is pretty close to the way stars move through the local sky of someone in Rhode Island. Stars will sort of rise somewhere in the east. They will come up overhead towards the south at an angle. At the highest point in their journey, they will cross your meridian, and then they will sink back down and they will set in the west. I kind of think of the meridian as kind of like the 12 o'clock hand. If the sky is a giant clock, the meridian is the 12 o'clock hand. It's where the star gets to its highest point. Okay. Last, because we're in the northern hemisphere, this is Rhode Island's local sky. If you go back to that slide I had a few moments ago, I don't know if that was slide 44 or whatever it was. No. If you're in Rhode Island in the northern hemisphere, you should be able to see the north celestial pole in your sky, and you should also be able to see the projection of the equator onto your local sky. Let's draw them in, okay? I'm going to use blue. I'm going to draw an arrow somewhere up towards the north. Let's label it NCP for North Celestial Pole. And let's remind ourselves that that's where Polaris is located. The celestial equator is a ring or an arc that must be at all times perpendicular or 90 degrees to Polaris. Now, I have trouble with this one. Usually the way I draw it is I try to make the best 90-degree angle I can, make a dot up here. So that's roughly at a 90-degree angle. And then I try to draw a ring from the west to the east, going through my local sky. It's not great, but that's the best I can do. That's your celestial equator, CE. Taken together, let's add these vocabulary terms down here, okay? North celestial pole and celestial equator. I defined those previously, so I don't feel the need to do it again. Taken together, the zenith, the horizon, the meridian, the north celestial pole, and the celestial equator are what are known as the fundamental positions of the local sky. In other words, once everyone understands what we mean by those terms, these are the terms that we use to reference the positions of stars and planets, and to do so properly. So these are necessary vocabulary words so that we have some guideposts on our sky. Otherwise, you're reduced to, you know, the star that's over there next to the little pine cone behind the tree. You know, we don't want to be doing that sort of stuff. We want to reference the geometry of the sky itself. Zenith, horizon, meridian, north celestial pole, celestial equator. Don't be shocked when you hear me start using those terms. All right. For the rest of our class, it depends how quickly we can move. I want to develop 3 coordinate systems so that we can describe stars moving through our sky. And I'm going to do some top-down structure with you so you see where we're going here. Does everyone have that? It's a lovely drawing, but I have to erase it now. All right. I don't know why I'm about to do this, but I feel compelled to take a photograph of it. Okay. I'm not even sure what that's about, but I have a feeling that's going to be useful to me someday. Okay. Yes, I want to see my work of art preserved forever.
Frame it.
I was kind of pleased with that one, to be honest with you.
It was a good one.
Yeah. We will do a tea break shortly, so I know you guys are getting fatigued. What do you say we crank out one more little mod? Oh, yeah, my timer's going to go off here. I think we got time for one more module, okay? Let's talk about what we're going to do with the rest of our day after tea break. We're going to develop 3 coordinate systems. I'm tempted to go through them quickly. We'll see. The first thing we're going to do is geographical coordinates. We need to review latitude and longitude because where you are on Earth determines not only what stars are visible, but it also determines the path that the stars take through the sky. The rotation of the sky from the North Pole is wildly different than the rotation of the sky in Rhode Island, which is wildly different than the rotation of the sky at the equator. So you need to know where you are on Earth before you can start to talk about how stars move through your sky. Then we'll develop 2 coordinates for the sky. The simple and basic one is called the horizon system. And it's just a very simple coordinate system to describe stars on the local sky. Eventually, we'll need a robust coordinate system, kind of like latitude and longitude for the entire sky, where stars will have roughly fixed coordinates. And that's the sort of professional equatorial system that astronomers use. And that's for the global sky. There are even other coordinate systems beyond these, like galactic coordinate systems, but we won't get quite that far in our class. These 3 will do us. And although this can be kind of boring stuff if you're a newbie to science, I will say that one of the cool things about this is if after taking this class, as I suspect you will, have more of an interest in these astronomy things, knowing this stuff will actually help you if you ever get a small telescope or want to do some basic observing. So this is actually kind of useful and practical stuff, if a little bit dry. Why don't we, before I get into it, because that's going to be a whole bunch of shit, maybe we'll start our tea break a little early, okay, at 1:40, because I just kind of need a little break here. 25 minutes. Do we want to indulge a bit? 25 minutes is enough time for me to get a sandwich, eat a sandwich, stare at the wall, and go, while drinking tea. And then I'm kind of like start to feel guilty, and then tea break is over. Okay, so do we like that? I think it's good for us to relax a little bit so that we don't get totally zapped, you know? These are long lectures. So I'm going to do my stopwatch thing again. This time I'll try to stick to it a little better. I'm setting mine for 25 minutes. And, oh, that's kind of cool. Whoa. All right. When I hit start, that will be our tea break, and we'll come back when it ends. Sound like a plan? Okay. Boom. So I'll see you guys in 25 minutes. Have a break. Over and out. All right. We're back. Here's our plan of action. Do the celestial coordinates. Do a lab on celestial spheres. Were you guys able to print out that lab sheet? I guess I should wait till lab to ask you about it, but Ian, Ryan, what's up?
For me, it still doesn't look like it's up.
It also is not up for me.
My B.
I also still like, I don't know where the USB thing went for me, but I just cannot find it. So I'll have to figure something out.
All right. Let me suggest something to you here. Let's open up the celestial. Oh, hidden from students. That's not helpful. Forget about the doc version. Let's open up the PDF. You know what you can do? Let me show you how this works, Ian. You can open it in Acrobat, and then you could fill it out digitally since we don't have too much math to do today. Open it in Acrobat Reader. You can choose fill and sign, and then you'll be able to add the name of your star, like Fun Star.
All right. Yeah, I was going to ask about a PDF editor, but then I was like, that really wouldn't work with math. But since you're saying there's
Acrobat Reader is free, so you could just use that.
awesome.
Remind me to remind everyone about that again at lab, because I suspect some people just skip the video and go right to lab. So even though shame on them, I should probably remind them that that's an option. A lot of people have issues with their printer from time to time.
Probably need to get like a new connector anyway, because
yeah, USB cables are a dime a dozen, right?
yeah, they only cost like $50. Thanks.
Oh my gosh, you gotta have a point, but get some cheap ones from China on Amazon or something.
Yeah, and they'll last all of 2 weeks. It's a give and take, you know.
Right. Okay. It's hot in here. I had to go to the store to get my sandwich, so. Let's start off with a review of geographical coordinates. I know the veterans know about this. Sage, maybe you know about this. New students won't necessarily know about this, but we'll try to be expedient since I'm covering ground that many of you know. Geographical coordinates. Oh, by the way, these geographical coordinates and other coordinates, they're angles. Don't forget that. The geographical coordinates are angles. We're used to conceptualizing latitude and longitude as a distance because we're stuck on the surface of Earth, but they actually measure angular displacements. Earth is a spinning ball. That gives the equator a unique line of symmetry, which breaks Earth into a northern and southern hemisphere. And that's a good system to develop. That's as good a line as any to develop our coordinate system around. So geographical coordinates are described by two angles. Latitude. Looks like I got the wrong marker here. There's no way I killed that marker that fast. It's really hot here, so maybe that's drying it out. Oh, here, sorry, there they are. Too many markers, guys, too many markers. Latitude and longitude. Latitude is defined as your degrees north or south of the equator. Longitude is defined as your degrees east or west of the so-called prime meridian. So latitude, which sometimes people remember being like lines of a ladder, latitude has horizontal ladder lines that measure north to south, all based on the equator. The equator is a natural 0 point, up to 90 degrees north at the North Pole, 90 degrees south on the South Pole. Longitudes run like tangerine slices through the Earth. They run north to south, but they are measuring east to west. There is no natural symmetry point from which to start. One line of longitude is about as good as any other. So astronomy people got together with their geology people, and they decided that the prime meridian would be a line. let's see if we can get a picture here, that runs through the front door of the Royal Greenwich Observatory, just outside of England. And the prime meridian is a line of longitude that runs right through the front door of the Royal Greenwich Observatory. It divides Earth into an eastern and a western hemisphere. A kind of cool, geeky thing to do is to visit the prime meridian, put 1 foot in the western hemisphere, 1 foot in the eastern hemisphere, and then take a little selfie pic for the gram, okay? In fact, one of my students must have done that because they returned after their vacation and awarded me my very own prime meridian pencil from the Greenwich Observatory gift shop. This is now a treasured item on my cart, and I won't let you borrow my prime meridian pencil. Okay, so send me gifts when you visit the prime meridian.
Actually, I think I went there when I was like 10 or something.
Are you serious?
Yeah, I didn't get a picture of me on the line, but I remember being there and my mom being like, that's the prime meridian. If you stand on one side, you're in the western hemisphere, and the other side, the eastern.
Very cool. Very cool. And of course, Ian, do you remember what we call the line opposite the prime meridian on the back end?
Is this dumb? Post meridian? No, okay. I don't remember. I probably have it written down somewhere, but
The international date line,
oh yeah.
right? The international, since Earth is constantly spinning, we have to decide where the day begins and where sort of Tuesday ends and Wednesday begins is opposite the prime meridian on the international date line. And it does a couple of wiggles. The good reason for having the international date line be the beginning of the day is it mostly cuts through water. It has to do a little jiggle dance around Fiji and Tonga. Otherwise, you could have a line cutting through a territory where it was Tuesday on one side of the street and Wednesday on the other side of the street. That could be awkward, right? But for the most part, it doesn't hit or cut through any major continents like the prime meridian does. So, stuff to know. It's useful to know Providence, Rhode Island's latitude and longitude. For Providence, Rhode Island, which is basically all of Rhode Island, our latitude 42 degrees north. Our longitude is 71 degrees west. Okay. As I mentioned at the beginning of class, it's kind of cool to use that compass app because you can get your latitude and longitude to a pretty high degree of precision. I'm actually standing at 41 degrees north latitude with 49 arc minutes and 34 arc seconds. Now, is anyone down in South County or far away from me? I'm in downtown Providence.
I'm on like College Hill, so I think we're
Oh, you're on College Hill?
Yeah.
Is everyone here kind of close to me then?
I'm over in Fox Point. I canceled location services on my phone, so I can't use a compass. But
you know what? You don't want Tim Cook tracking your every movement?
I mean, they can already do it pretty well. I don't need to give them any edge. It's okay.
Yeah. It's like they already know everything about me, but
Right.
Better.
It would be cool to see if in Fox Point versus the College Hill versus downtown, I bet there's a difference in arc seconds.
I bet there is. I was trying to get one earlier, and it just told me my phone didn't support it, so I kind of gave up. But
all good. I did this with a student yesterday, and she was in Johnston, and we were actually like 2 arc minutes off from each other. So being in Johnston is a couple of arc minutes from downtown, both in latitude and in longitude. So I suspect that if you guys are also kind of close to me, that we're probably differing from each other by arc seconds. There is a problem in the book that I thought about assigning that's kind of cool, where you work out what is 1 degree on Earth in kilometers, what is 1 arc minute in kilometers, and what is 1 arc second in kilometers.
Word. I found one that shows my latitude and longitude if you wanted to know.
So so let's compare notes here. So
can you read that? I got it.
well, let me
I
get that
cannot do
Logitech
that.
thing. All right, what are you at?
Oh, it looks like I am 10 arc seconds south, and let's see, about I have 23 arc minutes and 30 arc seconds for
Whoa.
my longitude.
Sorry,
I'm a
say that
little bit-
again. What's your longitude?
23 arc seconds and negative 30 arc minutes.
Wait,
Or I have that
don't-
backwards.
that don't make no sense.
I have that backwards. Negative 23 arc minutes and negative 30 arc seconds.
Wait, where's your not negative? You just have 20. Where's your negative coming from?
It has a little negative sign on it. I don't know if you can.
That don't make no sense to me. Oh, because it's eastward. Forget about the negative.
Oh, okay.
Just forget
Well-
about the negative.
23 and 30 for the last two.
So we're actually off by 2 arc minutes from each other?
Like 1 and some change. Yeah.
Oh, because it's 23 plus. Yeah, okay, so
Yeah.
we're about an arc minute apart. So from downtown to Fox Point is about an arc minute apart in longitude. Interesting. I would have thought it was less than that. That's interesting.
Me too.
Huh. Okay, cool. So fun with geographical coordinates. Let's do the horizon system next. The horizon system is a nice coordinate system to use when you're at the same telescope with your friend or your colleague, and you're both using the same telescope and you share the same local sky. The 2 angles it uses are, altitude and azimuth. Altitude could be defined as your degrees. Whoa, wow. Degrees above the horizon. So it's your degrees up from the horizon. If you want to get technical, it's degrees above the nearest horizon. Azimuth is defined as your degrees along the horizon. Now, if you're going to go degrees along the horizon, you have to have a starting point. Degrees along the horizon measured clockwise from north. All right. Let's just grab that picture of the local sky. Oh, my mouse is being funny here. Why is it sluggish? I think I need to get rid of this. Maybe my battery's dying. I don't know. Sorry, something's funny here. Wow, this is annoying. I just replaced these batteries recently too. I don't know if it's my computer running slow or what. Sorry, I'm losing it, guys. Oh, that's really irritating. I'm going to use this little mouse here. Okay. I don't love this picture because it's a little different than a local sky picture that we made together. Let's use the local sky picture that our 3D drawing was based off of, and let's go here. So let's say there's a star. I think that arrow there points towards the North Celestial Pole. Wow, this just started too. What do you think is going on? Oh, maybe it's Acrobat Reader. Something is messing me up. Forgive me, guys. The use of the mouse is kind of necessary. What is going on? All right, so I don't have any delay here. That tells me it is this thing. Okay, I'm sorry guys, can we stop share? Can we pause for a second? I just am not good using the track mouse, and I just need to change out the batteries. Just one sec. Okay, our mouse is back in action, situation resolved. I thought we would just do a quick practice with the Horizon system and then talk about its drawbacks. The nice thing about the Horizon system is that it's supposed to be wicked simple. You stand in the middle of a field or something, and then you see a star somewhere. Let's say that star is, I'll try to do this in 3D. Let's say that star is here. The first thing you do is you find the closest point on the horizon, which I'm guessing is like, in my case here. It sort of involves a little 3D thinking, right? So the altitude is just how many degrees up from the nearest horizon you are. So you start at the horizon, you go up. Someone give me a reasonable guess as to what that angle would be there. Just make up a number that's not totally crazy.
I mean, I don't know, maybe like 50 degrees.
50, 60 degrees, something like that. Yeah, less than 90, more than 45, right? So that's its altitude, it's its degrees up. The azimuth are the degrees along your horizon until you can get to that closest point. So what would be a reasonable guess as to the azimuth in this case?
I don't know, that could be like a 45. Like
Yeah.
halfway.
It's like halfway between north and east, so maybe a 45-degree angle. Good. So it's supposed to be simple. Degrees up from the horizon and degrees along the horizon. And a lot of times when you look up things like when will the ISS pass overhead, they'll tell you where it will appear, altitude and azimuth, kind of cool. So here's a couple of things to think about that's a drawback. The sky rotates every second. The sky is moving. And I know that if I don't have my tracking device set up for the telescope, if I take friends out and show them the moon through my telescope, I'll put the moon into the eyepiece so that it's perfectly centered. By the time I step away and say, go ahead and look at the moon's already drifted almost halfway out of the eyepiece. And if you think about the way the moon is moving just like any star or the sun. It's kind of moving along these kind of sideways tracks here. So at every moment of the night, a star is constantly changing both altitude and azimuth as it gets higher in the sky, and it's changing from east to west. So the altitude and azimuth are constantly changing. That's one drawback of the Horizon system. Another drawback is, well, what's good about the Horizon system is it's simple. And for this reason, people often design telescopes with altitude azimuth mounts. One of my favorite telescopes to dream about owning would be a plane wave 1 meter telescope, which retails for about $500,000. And here's a picture of that thing slewing around on an altitude azimuth mount. I know this is a pretty high power, sexy instrument. You can do all kinds of science research. So here they are demonstrating it in their offices. And you can see here the telescope has fork arms. Now it's dropping down in altitude, right? And it's rotating around in azimuth so that you can point at a star, which is cool because if you're at the telescope with your friends, say, hey man, I need you to point that at Arcturus. If they say, well, I don't know which star is Arcturus, you can say, well, that's easy. You want to go 30 degrees up, and then you want to go 40 degrees eastward from north, and boom, there's Arcturus, right? And a modern computer can make slight adjustments to altitude and azimuth so that even with an altitude azimuth mount, you can still track the sky. However, if you discover a cool object, like a groovy galaxy or a nebula, and then you want to name it after yourself, you're going to have to report the position of that to all these people who are not located in Providence, Rhode Island. And if you call up your colleague in, Tallahassee, Florida or something and say, hey, I want to tell you about this cool galaxy I discovered, the Brendan Galaxy. You can't tell them the altitude and azimuth for Rhode Island, right? Because if you go south to Florida, the positions of the stars will change. And it won't stay put, it'll keep moving. For this reason, we need a third coordinate system. And this third coordinate system it's basically going to be a latitude and a longitude for the celestial sphere itself. That way, when I discover a new star or a galaxy, I can report its coordinates and they will stay fixed and everyone will know how to find that thing. Does that make sense? All right. So the horizon system is what you use when you're just out at your telescope and you want to point around. But then you need a more robust latitude and longitude for the sky where everything kind of stays put. That's the equatorial system. Unfortunately, the equatorial system, as my returning students know, can be a wee bit confusing. Today I'll start with the definitions and then we'll talk about them. So you can think of the equatorial system as being good coordinates for what we would call the global sky. And they use two angles. One is called declination. Astronomers frequently abbreviate it as dec. Sometimes they even use a delta for declination. So sometimes you'll see the Greek letter delta representing declination. The other angle is called right ascension. And astronomers abbreviate that RA. So astronomers will refer to the RA and dec of a star. Declination is sort of like lines of latitude on the celestial sphere. Right ascension are similar to lines of longitude on the celestial sphere. Now the definitions. We don't use north and south for declination. We use positive and negative, but it's the same thing. And we don't use the Earth's equator, we use the celestial equator. So declination is defined as your degrees measured positive or negative from the celestial equator. Right ascension is a bit funny. What did I do with that globe? Wow, I'm really scatterbrained. Oh, I don't want to drop that thing. That's the issue. All right, check me out. If I take this ring here and I align it with the Earth's prime meridian, like I've done from my previous, I basically gave this lecture yesterday, right? As Earth spins and rotates, the prime meridian will sweep through different lines of celestial longitude or right ascension. So we can't choose the prime meridian or our coordinate system will be a rotating coordinate system. And those are messy, all right? Oh, we need to pick a point, some random arbitrary point on the celestial sphere to be our starting point. Do any of my returning students remember which point we choose as the starting point of right ascension?
Don't we use the spring equinox?
That's right.
You say I have it for all of the solstices and equinoxes, I think.
So, pardon?
Doesn't matter. Never mind.
We're going to do that too. Again, you're looking at the coordinates for all of them, but where do we begin, right? If you're going to design a coordinate system, you have to say, where is 0 going to be? Where is the start of my race? Where do I start measuring from? We will start measuring from the spring equinox. That's the point in Pisces where the sun is located on March 25th. It's also the point where the celestial equator intersects the ecliptic, okay? That's the spring equinox, a point on the sky. The other issue is that those star tracks that you saw earlier, stars only rotate in right ascension. They do not drift in declination. They only rotate in right ascension as the Earth spins. Because of that, it's actually kind of cool to measure right ascension in hours rather than measuring it in degrees, because then you can figure out how many hours it'll be until the star of interest rises or sets. Why can I use hours in place of degrees? Because it turns out that Earth spins 24 hours on its axis, and therefore Earth and the sky will rotate 360 degrees. If you divide 360 degrees by 24 hours, you get exactly 15 degrees per hour. That's not a coincidence. The Babylonians or the Egyptians or some ancient peoples, they designed the hour to be that way. Hours were invented to be a perfectly even 15-degree wedge of the sky. And therefore, in astronomy, there's a kind of kooky conversion factor that only makes sense to astronomers. And it goes like this. 1 hour is equal to 15 degrees of sky rotation. So as long as you're dealing in right ascension where the Earth is spinning, you know, Earth spins in terms of longitude, not in terms of latitude. This conversion factor makes sense. 1 hour is 15 degrees of sky rotation. So the definition of right ascension, if you kept it simple, is the hours of a star. How many hours away a star is. The hours of a star measured eastward from the spring equinox. And we don't just measure hours, we also measure in minutes and seconds as well. Which direction is eastward, class? I hope you remember that. Eastward is which direction?
Counterclockwise.
Counterclockwise. Nicely done, Sage. So let's go back and let's check out the star Arcturus that I had. Let me get out of here. Free publicity for Planewave. They ought to cut me a deal. They ought to get me a sponsorship where they give me my own 1 meter telescope in return for me promoting them. See, I got to think like you influencer kids. That's what I need to do, right?
We'll get you that telescope, I swear.
I want it. I want it so badly. Check out the star Arcturus in the constellation Bootes, excuse me. That'll come up in our lab today. You can see that it has, a right ascension. I think that one battery got me half there. Is 14 hours and 15 minutes. And look, they even break it down to 39.7 seconds. So that tells you how many degrees eastward from the spring equinox it is. The declination is positive 19, 10 arc minutes, 56 arc seconds. Remember how we did that in homework today? We formatted things like that. Yeah. Okay.
This is the stuff that confuses me the most out of anything I've done in last semester or this. Like I don't think I understand right ascension at all.
Well, it just takes a little bit of practice. That's all. Now, one of the things I usually do, and this is, we're not quite at 3 o'clock, but there is a couple other things I wanted to do today, but I'm going to be reasonable. We're at 2:45. Before we move on to do our lab today, I wanted to practice finding the equatorial coordinates of the 4 key points. But Ian, it sounds like you've got your notes from last semester and you're already kind of staring at them, right?
I'm going through and I'm editing and making sure everything is clear.
All right.
Because my notes.
Well, I don't know if that's still a useful exercise or not. It probably would be for Sage. And maybe the 2 Ryans will benefit from it. I'm sure some other students will as well. We can just do it faster if you already understand it.
Well, I'll not look at it so I can try and figure it out as we go.
Yeah, try not to look at it. That's my suggestion to you if you want to understand. You kind of just have to practice. Okay. Here's the point I'm trying to make, guys. Every single point on the celestial sphere should have a right ascension and a declination. Therefore, we should be able to describe the 4 key points on the celestial sphere using those coordinates, if we understand them as we think we do. So what I want us to do is I want us to try to figure out what's the RA and DEC of the spring equinox, the summer solstice, the fall equinox, and the winter solstice, okay? Let's do that as notes. It's a sample problem. Man, someone's grinding their fan belt up there. Okay, last bit for the day. I really should have gotten to Kepler's laws today, but we'll just do all that tomorrow, all right? Or Tuesday, rather, right? So here's an example. Find the equatorial coordinates, the right ascension and declination of the 4 key points in Earth's orbit that I began today's class with. So we'll have the spring equinox, the summer solstice, the fall equinox, and the winter solstice. Sage, you're gonna start us off because you're the only person who's new that I'm interfacing with, okay? Now, take it slow. You can give me either the RA or the DEC to start with. Let's focus on one of those 2 coordinates. And let's look at the globe for inspiration here.
Let's do the RA because it's easier. This is spring, right?
Yeah, it's spring equinox.
Yeah, let's do the RA.
All right, so what would the RA of that red point be?
I believe that would be 0
0 hours.
hours. Yeah.
Because we're on the spring equinox, right? So
Yeah.
normally here's how we format right ascensions, Sage. We format them like a military clock, 0, 0, 0, 0. It actually irritates me that Wikipedia doesn't do that, but whatever.
Okay.
All right, so that's, we always format right ascensions, hours and minutes, just like you'd see on a digital 24-hour clock. Okay, the declination is also easy, because what's the definition of declination?
The degrees measured from the celestial equinox. Oh, which is what it
Wait,
hit.
not celestial equinox, don't say that
Or
better.
equator. I'm sorry.
So if I'm on the spring equinox, I'm also on the celestial equator, so
Also 0
0 degrees this time.
degrees. Yes, I'm sorry. Units.
Okay, so Ian, you'll
Yeah.
find it's a little easier your second time through without looking at your cheat sheet.
Yeah. Yep.
Summer solstice.
So, I mean, it's kind of like a clock. So it would be 6 hours.
That's right, because it's a quarter turn, right?
Yep.
So from here to here is a quarter turn, that's 6 hours. If you go all the way around, it's 24 hours, right? Okay. So we have 6 hours right ascension, and how about the declination?
See, this was the part that was confusing me about this, that it just kind of clicked into place, is it has the dot for summer solstice on the celestial equator, but it's not there. It's down the 23.5 degrees.
No. You just said that all fucked up.
Okay.
The dot for the summer solstice is on the ecliptic, bro. Notice
Oh,
this is
yes, that's
tilted.
what I meant. That's what I meant. I'm sorry.
Okay. And it shows you the angle, right?
Yes. Yeah.
Declination are your degrees positive or negative from the
It
celestial
would be
equator.
negative 23.5 degrees.
Once again, the summer solstice is on the ecliptic, not on the celestial equator. What's fucking you up is that you want the celestial equator to be horizontal, but it is not in this picture. It's tilted.
Yeah.
So where do you get negative from? Usually,
Right. Okay, so we're looking at it from the celestial equator. I need to,
of
remember
course,
that. It's written down. That's the thing I need to remember. It's
Yep.
going to be positive 23.5 degrees because
Right.
it's above the celestial
Negative would
equator.
be in that direction, below the celestial equator, right? Okay,
Yes.
that's fine. All right, so you worked out a few kinks that were messing you up. So the right ascension, we had 6 hours. And for declination, we have positive 23.5 degrees.
Yes.
Ryan, Dick, you want to help us with the fall equinox?
Yeah.
What are you thinking?
Would the right ascension be 0 o'clock.
No. Remember, right ascension are hours measured eastward from the spring equinox. Eastward, as Sage reminds us, is counterclockwise. So we start at the spring equinox and we're going around counterclockwise until we get to there, right?
Yep.
So how many hours would that be?
Would that be 6 or
Six.
9?
How many hours does it take for the Earth to spin around the sky?
24 hours.
So a complete circle is 24 hours. It looks
12.
to 12 hours because it's on the other side. How about the declination?
Would that be 0?
Yeah, because it's on the celestial equator again. All right.
Yep.
I think part of what was confusing me as well is because, I mean, we looked at another star on Wikipedia and it was saying like the right ascension. Is that like saying the right ascension like now, or is
No,
it a fixed point?
Because it's measured in hours, you're thinking it's changing.
Yeah.
Right ascension is a fixed coordinate that happens to be measured in hours.
Okay, and a star would hypothetically move through that?
Move through it.
Like as the sky rotates?
No, they're fixed to the rotating sky. This is a really important point, so I'm glad we're having this discussion. The whole point of this coordinate system, Ian, is that if the right ascension of Arcturus is 14 hours and 15 minutes,
yeah,
that's it. It stays that. The sky might rotate. See, you're just messed up because you're thinking of the sun rotating and you're thinking of time changing. And so you see something measured in hours and minutes and you can't help but think it's flowing. But this is a fixed coordinate that happens to be measured in hours.
Okay. But, okay, the thing that was I got that, but the thing that was confusing me is that even though the star technically would be moving as the year progresses, it's still the same point.
Okay, hold on. Are you talking about its so-called proper motion, the star's hypothetical velocity with respect to the sun?
Maybe.
I don't think you even know what you're talking about.
No, I don't.
Right.
That's
So
why
I can't know what you're talking about either. So listen, let's pretend like the stars don't move.
Okay.
Because they kind of don't. They're so far away that even the closest, one of the closest stars to the sun, like Alpha Centauri or Bernard star, they might move 1 arc second in like 20 years.
Yeah, no, you're totally right. Yeah, I'm thinking about the sun is throwing me off. You're correct. We talked about that thing you just mentioned last semester.
Pretty much, if the right ascension of Arcturus is 14 hours and 50 minutes, we won't have to update that for at least 50 years.
Yeah.
And in 50 years, maybe it'll be 14 hours, 15 minutes, and 42 seconds or something. You know what I mean? It's yeah. But for the most part, don't start adding all this confusion on top of your already existing confusion.
Yeah.
The stars are fixed to the globe. Right ascensions are fixed to the globe. Like, you're about to do a lab on this, Ian. Look. Let me get out of share mode here. "14 hours and 15 minutes is like there. This whole line of longitude here is all for, it's hard to see myself from the screen. This whole thing is 14 hours and 50 minutes. That doesn't change. So if a star Arcturus is at +20 and 14:15, it's staying stuck there.
Yes.
That rotates with the sky.
Yeah.
Okay. Just don't confuse right ascension with time just because it's measured in hours, right? That's what's happening.
Yeah, I was confusing myself.
It's all right. These discussions help us. Hey, Ryan Spaveld, would you want to do the winter solstice for me? Since there's 4 of you, each one should do it.
That would be right ascension of 18 hours and a decadence of -23.5 degrees.
Nice. All right, cool. And for the benefit of new students, watching at home, let's see how he got that. He can see, where's my little arrow tool? If he starts here at the spring equinox, he's going around eastward or counterclockwise 6 hours, 12 hours to 18 o'clock. And then he's dropping for declination from the celestial equator down 23.5 degrees. Okay. At this point, we will conclude lecture for the day because that's a lot. And we will transition to our lab, which is short and easy. Do you guys have the printed materials? Or something you're ready to go, right? What do you say we kind of just get to it and we'll get it over with so we can get on with this beautiful sunny day, all right? I'll try to keep it short and sweet. We're just going to do the first 2 pages. It's so annoying. I printed them out yesterday and I scribbled all over them. I guess I have to print them out again. Why don't I pause the recording for 2 minutes while I transition my computer over to the lab bench, and that'll give me time to print out my sheets, okay? So 1 sec. Okay, students, welcome to lab number 2. For anyone just joining us, we are doing the second lab that is posted in the lab section of Blackboard. Click this lab tab and you'll see lab 2, the celestial sphere. I recommend downloading the celestial sphere's PDF, which looks like this. Today, we're only going to have time to do the first 2 pages. So just custom print pages 1 and 2. We don't need all the rest of it. One thing I mentioned, if you don't have a printer, today we're not going to be doing any real math calculations. So if you open that in Acrobat, if you don't have a printer, you could choose the fill and sign version. And you could enter the stuff we're going to need. Like, for instance, at the top, we want to put our name, right? We also want to put lab number 2. It's always important to do this so you know what you're submitting to. And later on, you have a record. Sorry, it's noisy. You have a record of which labs you did in case you need to dispute something with me, okay? For your lab section, you can just put AS1020 because you're the only 1020 section in this summer 1, okay? Now, we're going to be using this super cool celestial sphere to identify some famous stars and constellations. I'm probably going to use I just got a new iPhone and the camera's really good. So because we're looking at a translucent sphere, I want to do this. Hopefully I don't get too many embarrassing text messages during the course of this lab. Otherwise, I'm going to have to find a way to creatively edit those out. I don't, for the most part, most of them are PG-13, So hopefully.
I think you can mute specific conversations. Just don't forget to unmute them.
I tried putting it in airplane mode and the text still kept coming in. Maybe I have to turn off I don't care. I don't think anything bad's going to happen, so we'll risk it. My life isn't that exciting. Okay, in the first table here, we've been given the right ascension and declinations of the 10 brightest stars in the nighttime sky. So these are the most famous stars. They all have famous names. And our job is to find the name of the star in the constellation. Before we get going on that, it might be a good idea to just kind of review the constellation thing with you. Do you all remember how many constellations there are in the nighttime sky?
I think you said 88.
Very good. 88 constellations recognized by the International Astronomical Union. Constellations, of course, are little mythological stick figures, but astronomers also have blocked out areas of the sky that represent constellations. So the constellation of Orion is not merely the hunter stick man, it's this entire box territory which follows the stick figure in a complicated way. That way, every area, every piece or point on the celestial sphere falls within one of those 88 constellations. If I discover a star here, it would be in the constellation of Orion because it's on this side of the boundary, right? Okay, so that should make good sense to you. just like everywhere in the US has to be in one of the 50 states, everywhere in the celestial sphere has to be in one of the 88 constellations. I'm going to show you the boundaries in a second. Do I need to tell you anything else? No. Okay. So let's see how this goes here. I think I will, just to cut down on the chatter, go into airplane mode. And I think if I turn off iMessage, that should cut down on the distractions with my phone. It may even prevent some embarrassing thing. We'll see. Okay. Never know what's going to happen. So I'm going to go to share screen iPhone. Oh, I do need to activate Wi-Fi. Okay. Bam. Wow, this new phone just works so much better. The camera is really nice too, which is going to work out pretty well. Hold on, it takes a minute to connect. There we go. Okay, you guys can see my my paper here? Okay. So once again, you've got your name, lab number 2, AS1020. Let's get oriented with our celestial globe over here. Let me know if I'm too quiet to hear. Okay. Okay. All right, on this globe, you can see the seam of the equator represents the celestial equator, okay? Declination goes positive and negative from the celestial equator. Positive 10, positive 20, positive 30 declination, negative 10, negative 20, negative 30 declination. You can see they have the degree marks ticked off. The hours of right ascension are listed here. Hour 0, 1 hour of right ascension, 2 hours of right ascension. Usually you want to do right ascension along the celestial equator, but they do have some tick marks here. These big ticks are 20 minutes. The little tick marks are 4 minutes each, okay? Notice that the stars, like Alpheratz, are labeled in black. Alpheratz is this star. The constellation stick figures have these hard blue lines. The names of the constellations are in blue. Do you guys see these dotted blue lines here? Those are the boundaries of the constellations, which we would like to pay attention to, okay? This globe I should mention, and I'll come back to this point at a later time. This globe is a little out of date. These are beautiful globes that they don't make anymore. This was made in 1967 by the Triponese Planetarium Co. in Saginaw, Michigan. 1967 is almost 50 years ago. Earth has a very slow 26,000 year precession. It wobbles on its axis. And over long periods of time, this will change the coordinates of stars as well. So usually you've got to update these things every 50 years. For that reason, this is going to be a little out of date with the modern values, but it's going to be close enough. All right, let's look at, by the way, all these are backwards because you're supposed to like look through the globe and you're supposed to use like paper to read it properly. But honestly, I find it fine to channel a little dyslexia and just read it backwards, okay? All right. First star, 6 hours and 43 minutes, negative 17 degrees. Let's do it. So we'll rotate around here. This is a nice lab to do in person, but you know, COVID-19. Here's 6 hours. 43 minutes should be like where? That's 2040, that's 2044. So that should be 6 hours and 43 minutes. Negative 17 means go down minus 10 and down here. And what's our star? Unmute. Talk to me.
Serious.
Sirius?
Sirius. And what's the constellation?
Canis Molaire?
Major. Canis Major, which is the big dog. So they refer to Sirius as the dog star. It's the brightest star in the sky. And Canis Major is the big dog. Next up, 7 hours, 37 minutes, positive 5. So here's 7 hours. 37 minutes will be 20, 40. 40 minutes minus 4 minutes is 36 minutes, so pretty close to that. And then positive 5 brings us here. What do we got?
Procyon.
Procyon. In the
Procyon.
old Greek and Latin, C's were always hard K's. Procyon.
Yep. I should know that.
Oh yeah, are you the
Like
one
we
who
all took Latin, remember?
Yeah, I should be knowing that. And that's also
Canis minor is the
Oh.
little dog. Procyon and Canis minor. Taken together, the big dog and the little dog follow at the heels of Orion. This globe is all backwards, but as Orion marches through the sky, normally they're on the other, if you look through, can I do this? What's this look like? Okay. Here's Orion, and Procyon and Sirius are the two dogs. That was weird. They follow at the heels of Orion as he marches across the sky. So if you can find Orion in the wintertime, look to the left, you'll see Sirius below his foot and Procyon above his foot to the left. All right. Next up, 20 hours, 40 minutes, positive 45. So let's rotate back here a bit. Here's 20 hours. 20, 40 minutes is about there. Positive 45, 10, 20, 30, 45. What do you got? Talk to me, peoples.
Deneb.
Deneb in Cygnus, the swan. Deneb is the tail of the swan. In Cygnus. I have a little charger here. Hold on, guys. I gotta plug this thing in because I'm afraid my phone will die. So many damn wires. My whole life is just wires.
I say, if you could see the floor next to me right now, it pretty much looks like that.
I know. One day I'll tell you my laws of wires that I invented. You know how like Kepler has 3 laws of planetary motion, and Newton has 3 laws of motion, and Kirchhoff has 3 laws of radiation. I decided that I would invent my own 3 laws of wires. Are you ready for them? It goes like this. A wire will tangle with itself is the first law. The first law of wires is a wire will tangle with itself. The second law of wires is a wire will tangle with any object in its path. And the third law of wires is any 2 wires that come in contact will tangle.
So when are you publishing the Principia wires?
I know, I really need to. The Principia fuck shit, where I just have some
Submit it to science.
bottom knots, yeah. Okay, moving on to our next star, 1948 and positive 9. Okay, so here we go. So we have 1948. Positive 9 brings us up here. What's that guy say?
Altair?
Altair.
Okay.
Altair, and that's Aquila the eagle. Okay? Altair, I think, is the eye of the eagle or the beak. You'll notice that the names of many of these famous stars are Arabic, because during the Middle Ages, Arabic astronomers preserved the Greek astronomy and the names of the stars and things like that. Pretty cool. And Aquila the eagle. Okay. Okay, next up, 513, right ascension, positive 46. let's wing back over here. (513) is probably about here. It's about 3/4 of the way. Positive 46, 10, 20, 30, 46. Capella is the star. Let's see, what's our constellation here?
Is that Auriga?
Auriga.
Auriga. Hey, Macarena.
Capella is the goat. Auriga is a herdsman carrying the goat. So, so this is Capella, and these three little stars are called the kids. I don't know. You see it on the nighttime sky sometimes. All right, next up, 513, same right ascension, this time down -8. So 513 we decided was about 1/4 of the way between 5 and 6. -8 brings us down here. Notice that we're in the constellation of Orion. Saif is the left foot. The right foot is Rigel, and that's where we are. The blue foot of Orion, Rigel. I'm going to jump over 14 because this guy is close by, all right? Just to speed things up. 553 and +7. 553 is about there. +7. What do we got?
Betelgeuse.
Betelgeuse. Nice. Make sure you skip a line here. All right. Now let's go to 1410. So I'll rotate around here. There's a little hole here, and if it pops through in the wrong way, I can end up knocking this whole thing over. So these are quite expensive, and you can't get them anymore. So I have to be real careful. They're such a cool learning tool, though. This is of the finest quality in craftsmanship. 1410, 48, it's about there. +19. Oh, we recognize this guy, right?
Arcturus.
Arcturus. You can find Arcturus in your nighttime sky by following the handle of the Big Dipper. They say that if you can find the handle of the Big Dipper, you arc to Arcturus. Arc through the handle of the Big Dipper. Arcturus will be up in your sky tonight, by the way. It's a sort of bright yellowish star. And what's the name of that constellation there?
Botez.
Pardon?
Botez.
Bootes. There's actually an umlaut. It looks like booties, but it's Bootes. And B-O-O, second O has an umlaut. Bootes. Bootes is also a herdsman. Notice how all the constellations, they're all agricultural things, right? Herdsmen, eagles, dogs, you know? It's an agricultural society that developed these constellations, which is cool to think about. Yeah, makes you think. 1627, -26. So here's 16, 27 is probably here. -10, excuse me, -20, -6.
Antares.
Antares is anti-Mars. It's a red star that gets confused with, it's Antares, Antares.
That's
And that's in
awesome.
the constellation of Scorpius.
I like that they went Greek with it instead of Roman. Get at it. Yes.
Yeah. And that's in Scorpius. All right. Ryan's still there. He's just cut off in my recording. Okay. One more here. 1836, positive 39. 18, 20, 24, 28, 32, 36, and positive 39. 10, 20, 30, almost 40. Our star is Vega and the constellation Lyra the Harp. These are the 10 brightest and most famous stars in the nighttime sky. Okay, I'm going to have us do two more short exercises. In the next table, they ask us to find in what constellation are the planets located tonight, okay? Now, to do this, it's often helpful to make use of an ephemeris table. An ephemeris table would be, in the olden days, a book where they would publish the positions of stars as calculated by some astronomer. Of course, today we use high-powered computers to do this work for us. So the ephemeris is now, oops, sorry, I lost it. Basically,
was it
a computer.
like the almanac?
Huh?
Was it like the almanac?
Kind of like an almanac, but for astronomers. That's how you would think of an ephemeris, right? And they have here the right ascensions and declinations. The 5 naked eye planets, the ones that you could see with your naked eye that were known to ancient astronomers: Mercury, Venus, Mars, Jupiter, and Saturn. Now, they don't print these things on the globe. Why not? Why aren't the planets printed on the globe?
Because they move.
Because they move around with respect to the background stars. So these are the coordinates of the 5 naked eye planets tonight. Let's write them down on our papers here. See if you can follow along with me. Let's just jot down their coordinates and then we'll get the constellations. So I'm going to make a little sort of mini table here. So here's RA and DEC. Okay, so for Mercury, it's 536 and positive 24 degrees. Venus is 529 and positive 24 degrees. Huh. They're pretty close to each other. Mars is 731 and positive 23 degrees. Jupiter is 2214 and negative 12 degrees. Saturn is 2104 and negative 17 degrees. Let's find those constellations. You guys got that? All right, let's go for Mercury. 536, positive 24. Oh, sorry. I want to be able to see you guys on my screen so that I can monitor how this is going. Oops. Come on. All right. Sorry. 536, positive 24. So 530 is about halfway in between. And positive 24, 10, 24. Taurus, right? I suspect the next one will be as well. 529 and positive 24. Notice how close those two planets are to each other. They are in conjunction. When two planets appear in roughly the same position in the sky, we call it a conjunction between two planets. Mars, 731, positive 23. Here's 7. 30 is about in the middle. Positive 10, positive 20, 23. Gemini. Do you guys notice something about the constellations in which the planets are found?
It's all the astrological constellations.
Right, they're the zodiac constellations. And why do planets appear in the zodiac constellations?
Because they're on the ecliptical going around the sun.
They're on the ecliptic in the same plane as Earth because the solar system's a disk. And the disk of the solar system is the ecliptic, which is the zodiac. Nice use of your knowledge. 2214, negative 12. Just flip this around. Okay. 2214 is maybe a quarter way through. Minus 10, minus 12 puts us in Aquarius. Aquarius. Okay. Let's see about Saturn. That's kind of close. 2104, negative 17. So 2104 is really close to 21. And then minus 10, almost minus 20. Looks like we're in Capricornus. Now, for these coordinates, this would have been the constellations in which they appeared had this been 1967. It's been about 50 years, and even though Earth only changes its position of its axis tilt every 26,000 years, 50 years is enough time where a little bit of drift starts to come in there. For instance, let's look at the computer program that I looked up today actually gives us for the actual constellations. Notice, sorry, can you guys see my screen here through my phone? Notice that they're a little bit different. Mercury and Venus are still in the same constellation, but it's Gemini. Mars is in Cancer, Jupiter's in Pisces and Aquarius. They all seem to have drifted by about one constellation, right? So, you know, I'm pretty sure, yeah, instead of being in Capricornus, it's drifted back to Aquarius. And so over time, the right ascensions do shift their position along the stars just because of the fact that Earth is very slowly wobbling on its axis. I want to have us do one more exercise together. And this should be pretty easy based on what we did for our last exercise, right? What we're trying to do here is move the sun to the dates along the ecliptic. Here you can see the dates of the ecliptic. This little nubby represents the sun. And we move the sun along the ecliptic, and then we're supposed to read off the RA and DEC. We have some arbitrarily chosen dates, like March 21st. Here I've moved the sun to March 21st. What is the right ascension and declination of the sun on that day?
0 and 0, right?
Yeah. So for the right ascension, it's 0 hours. For the declination, it's 0 degrees. And you guys did this for the last thing in class. Here you can see it's on the celestial equator. It's on 0 hours. Okay. Now we slide over to June 21st. You might even be able to guess what it's going to be.
6 hours and 23.5 degrees positive.
Yep, and then you have to go up, 23.5 to get to the sun. Okay. There was a reason I had us do that exercise, was to speed up our labs too, okay? So now we'll go over to the September 21st. What do we have here?
12 hours and 0 degrees.
Mhm. December 21st.
That would be 18 hours and negative 23.5 degrees.
Notice this thing doesn't quite perfectly line up with where it's supposed to. It's, you know, imperfect. 18 hours, negative 23.5. Let's see if we can estimate today's. Today is 5/27, right? So that's May 27th. Whew, I almost knocked this thing over. All right, so there's May 20th. So May 27th is about right there. What would you estimate its right ascension to be?
That's, I mean, I can see the 65 degrees.
No, that's along the ecliptic. That's degrees along
Yeah.
the ecliptic. We want its declination and its right ascension. Let's do its right ascension first.
Is that 420?
420? It's kind of
Is it?
close, right?
Isn't it?
Is that what that is?
Wait, hold on.
Looks
4
like it says
hours.
460, but that can't be right.
Wait, 4 hours and 4 minutes, 8 minutes, 12 minutes. I'd say 4 hours and 12 minutes is closer.
Oh, I
420.
thought they were dashes of 5. Okay.
No, it's because the big dash is 20 minutes, so the little dashes are 4 minutes each.
Oh, my time frames were all messed up.
No, it's okay. It's a weird increment, but they took a 20-minute interval and they divided it by 5, so each one has to be
That
4
makes sense. So you can get closer. Yeah.
So 412 maybe 416. We'll go with 416, 12, 13, 14, 15. Yeah, we'll go with 12, 16. I'm sorry, wow, 12, 416, right? How about the declination?
That's like right on 10, isn't it?
Wait,
Oh,
that's
20.
0. Positive 10,
Positive 20.
So
positive
20?
20, positive 21 or something.
Yeah.
Let's see how it compares to the actual coordinates of the sun today, as reported by ephemeris.com. The sun is at the top, 4 hours and 19 minutes, positive 21 degrees. We didn't do too bad, did we?
No, that's pretty
Pretty
accurate.
close.
Yeah, not too bad at all. We were off by 3 minutes of right ascension, and we pretty much nailed the declination. That's nice. Okay.
Could you say
Why did these come out so accurate? Because the precession doesn't really change the relative position to the ecliptic. That's still always going to be inclined by 23.5 degrees. The stars, however, get jostled around a bit. Let's do one final exercise for fun. It's often said that your astrological sign is based upon your sun sign or the location of the sun on your birthday. However, most of those zodiac signs were calculated using Ptolemy's Tetrabiblos written in 50 AD. Since then, there's been a whole fuckload of drift between the stars. So Sage, for instance, what is your birthday as a month/day?
I am May 22nd, actually. I'm a Gemini.
Okay, so his putative sign, the sign he is supposed to be, is a Gemini. Let's travel to May 22nd and find out where the sun was in your birthday. Well, it's basically where we just were. In what constellation was the sun on your birthday?
That's Taurus.
So, in other words, your real sign is a Taurus.
Interessante.
So think about that, right?
Is
Okay.
it just skipping back one? Or is it?
Yeah, it looks like it's drift. It's for most people, every now and then, because the constellation Leo, for instance, is really, really long. It
Mhm.
doesn't, sometimes people will be a Leo and they'll still be a Leo when it look, they'll be like, see, I told you so. And then
Yeah.
it's like, ah,
So close.
so it's drifted probably by about 2 months or so.
Okay.
Uh,
That's interesting. I used to go to college in Burlington and I lived with 2 vegans, so I know all about it now.
exactly, yeah. I bet
But
I bet there were a whole lot of crystals hanging in your window.
oh, you have no idea.
And
You
some
have
matcha
no
powder
idea.
cupboards.
We have mandalas for days. We got it all. Like
Honestly, it's not that it's really a terrible way of living. It's just the mumbo jumbo that gets to you,
it's
really.
cute. It's just not proven.
Or rather, it's totally disproven.
Yeah.
It's totally
fun.
proven
It's just-
to be false.
It's fun. It's just
Yeah.
when they try to start to dictate your relationship with them based on it is when I'm like, all right,
Yeah.
Nobody likes a zealot, that's for sure.
Yeah.
Okay, so and we've done this before with the rest of you guys, so I think I've made my point. Although anyone who watches at home later on is welcome to ask me to look up their true sign, and I'll be sure to tell you based on your birthday. Okay, so this is what we're going to turn in. We're going to turn in that page, and we're going to turn in that page, and that should be it, okay? Submit them to Lab 2 as soon as possible before you forget, right, Ryan Spavold? You're not going to pull that shit you did last
I'm not
time?
gonna forget. Don't worry.
Okay.
I won't forget.
Awesome. So get right on that, and the rest of you at home, submit those too. Remember, everyone, the deadline for this week's submissions. So this week, you now owe me Lab 1, Homework 1, and Lab 2. I'm going to grade them Sunday night at 11 p.m., and then it's closed out, and I will deactivate them. All right? So please get it in by then. Otherwise, have a great weekend. Enjoy this sunny day, and I guess I'll see you guys next Tuesday. We will meet at 10 a.m.-ish for our Homework 2 session, okay? Did that work today for everyone?
Yeah, it was nice.
Yeah.
Yeah,
I'm
Yes.
gonna be recording as soon as it's up.
Yep, and I'm going to lift this recording will probably be close to 5 gigs, so it's going to take 2 hours to render and another hour to get up there. So I'll get it up as soon as I can.
Quick question right before, I don't know if anyone here knows. I'm editing it in Acrobat. Do you know how to like trim off the pages that we're not using just so I'm not submitting blank stuff to you?
That's okay. Ian, it's okay.
Okay, cool.
I made a thing about it with Ryan earlier, but since you don't have a printer, just you've done enough today. Just submit it.
Okay.
Thank you. Can I ask you two kind of fully loaded questions?
Totally.
What do you think about the temperature difference in the cosmic microwave background? And also, what's your opinion on quantum entanglement?
The cosmic microwave background is really cool, right?
Mhm.
Because those little microscopic fluctuations, which are probably like, they call them these like little seeds, small thermal differences in the temperature of the photon particle bath just after the Big Bang. Those things influenced how dark matter contracted, and they led to the seeds that built up galaxies. If it hadn't been for those tiny fluctuations in temperature, those enhancements in density, dark matter wouldn't have pooled the way it did, and we wouldn't have had enough gas to form galaxies, or enough concentration of gas to form galaxies and then stars. So those little bubbles, in some way, they were the seeds that formed all of the cool stuff in the universe, like galaxies and stars. And it's really cool to learn a lot about astronomy and track the history of how we went from the Big Bang to the current universe we have. Quantum entanglement, particle physics is one of my rustiest areas of physics, but it's amazing to me because this class we're going to cover relativity in one of our later lectures. So I'm going to have a whole lecture on both special and general relativity. It's one of my favorite subjects. One of the rules of physics related to relativity is that you cannot travel faster than the speed of light.
Mhm.
However, there are also rules associated with quantum mechanics. If you have an electron with spin up in your helium atom, the other one has to be spin down, and particles can become entangled in such a way. What's fascinating to me is, from what I understand, most of our modern experiments show if you have two entangled particles, say one with a spin up and the other spin down, and you separate them, flipping the spin of one somehow seems to instantaneously flip the other faster than
Yeah,
the
I
speed of light.
like just read an article about this, and I was like, what?
Could we use quantum entanglement to, I mean, spin up and spin down, those are ones and zeros in computer programs. That's the idea of quantum computing ultimately wants to use the spins of particles as the digital transistors of the future, which means
Yeah.
computers are going to get stupid
Super
smart.
fast.
Like,
Yeah,
like pretty soon we're going to be working for them, you know?
yeah.
So, and let's
Sure,
hope they want to keep us around and feed us.
Straight
Uh,
dystopian.
yeah.
Yeah, thank you for your input on that. I had
Yeah.
a philosophy class last semester, and he kind of just like dropped a super biased CMBD like video that was like, is predestination real? And I was like, I want to talk to someone who knows like about this, about that. Like,
Yeah.
yeah.
There's a lot of philosophy stuff about free will versus determinism, based on the fact that the universe is made of physical laws and some of them are predictable. You know,
It was kind of up in the air.
free will is,
But-
I don't know if I totally believe in it really, but
yeah.
certainly you have the illusion of free will, and sometimes the illusion is just as good. There's this famous Harvard psychologist, Dan, it's not Dan Flavin, it's something like this, and he does these experiments in psychology where a person will watch a video of themselves and a second person will put their arms through their arms, and they'll watch a video of somebody else's arms picking up a glass and drinking it. And the person knows it's not their arms going through. And afterwards, they'll interview the people and be like, why did you drink that glass of water? And the person will be like, I don't know, I was thirsty. Like, the moral of the story being like, just watching a video of yourself where you know you're not the one who took the drink of water, you will still interpret it as free will, as if you wanted to do it. And his suggestion is that people will just say any old crazy shit so that it seems like what's going on in their head will make sense, right? Nietzsche has a very cool saying, the philosopher Nietzsche, about Descartes' I think, therefore I am. At some point he says, when are people going to wake up and realize, I don't think, it thinks. Love it. Okay. Anyways, some of these things are a little over my pay grade. You might want to ask your philosophy professor about it, but they're certainly cool to read about, and they are connected to physics. And you'll see, Sage, that as this semester goes on, we'll get away from the quotidian world of stellar coordinates, and we'll get into some of those weird philosophical things too. So there'll be time enough for that. Okay.
Nice.
All right. You guys have a sick weekend, and I'll be hanging with you come Tuesday at 10 a.m.
Sounds good. Have
All
a good
right.
one.
Bye. Over now.